Look up at the night sky, and you see a scattering of single, distant points of light. It is a beautiful, serene, and deeply familiar sight. But if you could peer a little deeper, beyond what our eyes alone can perceive, you would discover that the universe is far from a solitary place. Out there, in the vast darkness, the true cosmic dance is a complex, swirling ballet of multiple partners. We are all familiar with the idea of binary stars, two suns locked in a gravitational embrace. But what happens when you add a third? What strange and violent beauty emerges when gravity's delicate dance involves not two, but three stars? The answer is a chaotic, unpredictable, and utterly fascinating realm that challenges everything we think we know about how solar systems form and evolve. Welcome to the enigmatic world of triple star systems. These cosmic configurations are not just rare curiosities. They are extreme laboratories where the fundamental laws of physics are pushed to their absolute limits. Imagine a solar system with not one but three suns in its sky. Some might orbit each other so closely they appear as a single, brilliant star, while a third loops around them in a wide, slow-motion pirouette that takes centuries to complete. In other systems, all three stars might be locked in a frantic, unstable dance, constantly tugging and pulling at one another, creating gravitational tides so powerful they can rip planets apart or fling them into the cold depths of interstellar space. It is within these turbulent environments that astronomers have made some of the most bizarre and mind-bending discoveries, findings that rewrite the textbooks and force us to reconsider the very possibilities of life in the universe. In this video, we are embarking on a journey to explore 50 of the strangest, most astonishing revelations about these cosmic oddities. We will venture to systems where the suns never set, where planets orbit in figure-8 patterns that defy common sense, and where the very fabric of space-time is warped by the immense gravitational forces at play. We will uncover how these systems birth planets against all odds, and how they might ultimately tear them apart. This is a story of cosmic chaos and unexpected order, of destruction and creation on a scale that is almost impossible to comprehend. So prepare to have your understanding of the cosmos expanded, because the reality of triple star systems is far stranger and infinitely more wonderful than any science fiction. Let's begin our countdown. Our journey into the strange begins with a discovery that turned science fiction into scientific fact. For decades, the iconic image of Luke Skywalker gazing at a double sunset on Tatooine captured our imagination. But what if a planet could experience not just two, but three suns in its sky? Astronomers found exactly that in a system known as HD 131399, located about 340 light-years away in the constellation of Centauri. There, a young, massive planet, designated HD 131399 AB, orbits in a gravitational environment of staggering complexity. For about half of its 550 Earth-year-long orbit, an observer on this world would indeed experience triple sunrises and triple sunsets, with all three stars visible in the sky at once. It is a spectacle that makes Tatooine seem almost mundane by comparison. The sheer existence of a planet in such a system is a triumph against incredible odds. The gravitational dance here is a delicate and precarious one. The system is arranged with two stars, let's call them star A and star B, orbiting each other quite closely. This binary pair is then locked in a much wider orbit with a third, more massive star, star C. The planet itself orbits the largest star, star C, at a tremendous distance, roughly twice the distance that Pluto is from our own sun. At such a far remove, the gravitational tugs from the inner binary pair of stars become a constant threat to the planet's stability. A slight miscalculation in the balance of forces could easily send the world careening out of the system entirely or plunging it into a fatal embrace with one of its suns. Detecting a planet in this chaotic ballet is a monumental feat of astronomical ingenuity. Astronomers primarily use a method known as direct imaging, which is like trying to spot a firefly next to a massive, blazing spotlight. They use advanced instruments on telescopes like the Very Large Telescope in Chile to physically block out the overwhelming light from the stars. This allows them to see the faint, warm glow of the planet itself. It is a technique reserved for young, hot, and very large planets' worlds that are still glowing with the heat of their formation. The success of this method in a triple system tells us that planet formation is not only possible but perhaps even resilient, occurring in some of the most gravitationally hostile environments imaginable. What does the existence of HD 131399 AB and other similar worlds teach us? It fundamentally expands our understanding of where planets can form. For a long time, we assumed that the quiet, orderly suburbs around a single star were the most likely nurseries for planetary systems. The discovery of planets in triple star systems proves that planet formation is a robust and widespread process, capable of persisting even within the gravitational whirlwinds of multiple stars. It suggests that planetary birth is a force of nature that can thrive amid chaos, carving out stable orbits where logic says none should exist. This single discovery alone challenges our planetary prejudices and opens up a vast new array of possibilities for what might be out there, waiting in the light of multiple suns. Moving from the seemingly stable spectacle of triple sunsets, we must confront a deeper, more unsettling truth about these systems. The beauty of HD 131399 AB's orbit masks an underlying reality of profound gravitational turmoil. While that planet has, for now, found a precarious balance, the stars themselves are engaged in a dance that is fundamentally chaotic and unpredictable. This brings us to the core reason why triple star systems are such extreme environments, the infamous three-body problem. Unlike the two-body problem, which Sir Isaac Newton solved centuries ago, allowing us to predict with perfect accuracy the orbits of two gravitational bodies like Earth and the Sun, the three-body problem has no general, stable solution. When you introduce a third massive object, the elegant equations of motion break down into a swirling maelstrom of complexity. The heart of the problem lies in sensitivity. The future path of three stars orbiting one another depends so exquisitely on their starting positions, masses, and velocities that even the tiniest, immeasurable difference, a variation smaller than the width of an atom in their initial setup, will lead to wildly different outcomes over time. It is a system built on a knife's edge. This is not a limitation of our mathematics or computing power. It is a fundamental property of the physics itself. We can simulate these dances, but we can never precisely predict their final fate billions of years into the future. They are, in the truest sense of the word, chaotic. This inherent instability has a dramatic and violent consequence: stellar ejection. In a significant number of triple systems, the complex gravitational tug of war eventually reaches a boiling point. The stars exchange energy in a frantic ballet, and one star, often the least massive of the three, can be slingshotted away with tremendous force. Imagine a game of cosmic pinball where the flippers are the other two stars and the ball is sent hurtling out of the machine entirely. This ejected star becomes a runaway, a solitary traveler flung into the darkness of interstellar space at incredible speeds, leaving behind a more stable and now binary star system. We have observational evidence of this dramatic process. Astronomers have identified hypervelocity stars racing through our galaxy, their speed and trajectory suggesting they were violently expelled from a dense stellar environment, very likely a triple system at the heart of a star cluster. Furthermore, we see binary star systems where one star is a white dwarf or neutron star, the dense corpse of a dead star, and its companion is a main sequence star. The presence of such an old, evolved star alongside a younger one is a strong clue that a third star was once present. Its gravitational interactions sped up the evolution of the older star before the trio's unstable dance culminated in the third star's ejection, leaving the odd couple behind. This process of ejection is not just a celestial curiosity, it has profound implications for the galactic ecosystem. These runaway stars carry their chemical enrichment with them, seeding different regions of the galaxy with elements forged in their cores. They can plow through interstellar gas clouds, potentially triggering new waves of star formation in their wake. The triple star systems that survived the ejection event, now pared down to a stable binary, are permanently altered. Any planets that may have been forming in the system have their destinies rewritten in an instant, their orbital architectures scrambled by the sudden, violent departure of a sun. The unstable dance of gravity in triple systems is therefore a primary engine of change, a mechanism for redistributing mass and energy, and a reminder that the cosmos is a place of both creation and cataclysm. Just when we think we have a star system figured out, the universe loves to throw us a curveball, and few curveballs have been as surprising as the one delivered by one of the brightest stars in our sky. For centuries, Fomalhaut, the brightest star in the constellation Piscis Austrinus, was a solitary beacon known as the Lonely Star because it shone with such prominence in a relatively empty patch of the heavens. Then, in the late 19th century, astronomers discovered it had a companion, a smaller star orbiting at a great distance. Fomalhaut became a binary system, a fascinating but not entirely unusual configuration. But the story was far from over. In the 21st century, advanced telescopic observations revealed a stunning truth. Fomalhaut is not a binary at all. It is a wide triple star system, and the discovery of that faint, distant third member has completely rewritten the history of this cosmic neighborhood. The key player in this cosmic reshuffling is a dim red dwarf star named Fomalhaut C. It orbits incredibly far from the brilliant primary star, Fomalhaut A, at a distance of about 2.5 light-years. To put that in perspective, that separation is nearly twice the distance between our Sun and its closest stellar neighbor, Proxima Centauri. For so long, Fomalhaut C was simply overlooked, lost in the glare of its brighter sibling, and so far away that its gravitational connection wasn't immediately obvious. Confirming that this faint speck of light was indeed part of the same system required precise measurements of its motion across the sky, proving it was gravitationally bound to Fomalhaut A and its closer companion, Fomalhaut B. This discovery transformed our understanding from a simple binary to a far-flung stellar trio. This reclassification wasn't just a matter of updating a star catalogue. It had profound consequences for the most famous feature of the Fomalhaut system, its enormous, brilliant debris ring. Fomalhaut A is surrounded by a vast belt of dust and ice, often compared to our own solar system's Kuiper belt, but on a much grander and more spectacular scale. This ring is strikingly sharp-edged and offset from the star, characteristics that had long puzzled astronomers. With only Fomalhaut A and B in the picture, the gravity shaping this ring seemed insufficient to explain its precise, eccentric structure. The introduction of Fomalhaut C into the equation provided the missing gravitational architect. The subtle but persistent tug from this distant, third star over millions of years is now considered the most likely force that sculpted the debris ring into the narrow, elliptical shape we observe today. The ripple effects of this discovery even extend to one of the most debated exoplanets in recent memory, Fomalhaut B. Initially heralded as one of the first exoplanets ever directly imaged, this object appeared as a bright dot moving just inside the debris ring. However, its behavior was bizarre. Instead of dimming as it orbited, it grew brighter, and its path didn't seem to be strongly influenced by the gravity of Fomalhaut A. The existence of Fomalhaut C helped solve this mystery. Astronomers now believe that what was observed was not a giant planet at all, but a colossal cloud of fine dust particles, likely produced by a recent, violent collision between two large planetesimals. The gravitational perturbations from the entire triple star system, including the distant Fomalhaut Sea, could have orchestrated the orbits of these bodies, setting them on a collision course and creating the ephemeral expanding dust cloud that we misinterpreted as a world. The tale of Fomalhaut is a powerful lesson in cosmic humility. It demonstrates that even the stars we think we know best can hold profound secrets. A system we viewed as a simple binary for over a century was in fact a complex gravitational trio whose members, separated by light years, still communicate with each other through the invisible force of gravity, shaping dust rings and potentially triggering catastrophic collisions. This discovery forces us to ask how many other binary systems in our galaxy are actually hiding wider, fainter siblings, their gravitational influence silently sculpting the architecture of planets and debris from the dark outskirts of their stellar homes. This revelation about Fomalhaut forces us to confront a much larger and more humbling cosmic truth, one that fundamentally reshapes our place in the universe. We have long viewed our own single-star solar system as the standard model, the typical arrangement around which the galaxy spins. But what if our quiet, solitary sun is the real cosmic outlier? This brings us to a discovery that is less about a specific strange system and more about a radical recalibration of what is normal. Recent, extensive astronomical surveys have delivered a staggering conclusion. Triple star systems and multiple star systems in general are not the rare oddities we once thought. In fact, they are astonishingly common, perhaps even the rule rather than the exception, especially for certain types of stars. The evidence for this comes from painstaking statistical analysis of the stellar population within our galaxy. Projects like the Sloan Digital Sky Survey have meticulously catalogued the light from millions of stars. By analyzing the spectra of this light, essentially, the star's fingerprint astronomers can detect the subtle wobbles or shifts that betray the presence of unseen stellar companions. When you compile this data on a massive scale, a clear pattern emerges. While it is true that the majority of stars are actually solitary red dwarfs, when we look at systems like our own Sun, which are more massive and luminous, the story changes dramatically. For Sun-like stars, and even more so for the massive, brilliant O and B-type stars, being in a multiple system is the norm. Studies now suggest that for these massive stars, the percentage residing in double, triple, or even more complex systems could exceed 70, 80, or even 90%. Our solitary Sun, it seems, is in the minority for its class. This newfound commonality forces a complete rethink of the planet formation process. For decades, our models for how planets coalesce from swirling disks of gas and dust were built around the calm, orderly environment of a single star. The chaos of multiple stars was considered a complicating factor, a disruptive influence that would prevent the delicate process of accretion from succeeding. But if most stars that are like our Sun are born into multi-star families, then our models are based on a special case, not the average one. Planet formation must be an incredibly robust process, able to proceed not in spite of the gravitational turbulence but within it. The existence of planets in systems like HD 131399 AB is no longer a bizarre exception. It is a testament to a universal and resilient phenomenon that operates under a wide range of conditions. The implications of this are profound for the search for life beyond Earth. Our definition of a habitable zone, that narrow region around a star where water can exist as a liquid on a planet's surface, becomes infinitely more complex in a triple system. A planet would receive light and heat from 3 different sources, creating a habitable zone that is not a simple, stable ring, but a dynamically changing region that pulsates and shifts as the stars move in their orbits. A world might spend part of its year comfortably warmed by all 3 suns, only to later find itself in a temporary deep freeze as it swings to the far side of its orbit relative to the main heat sources. Life would have to be incredibly hardy to survive such dramatic climatic swings, but the sheer number of these systems means the raw real estate for potential life is far greater than we ever imagined. This shift in perspective, from seeing triples as curiosities to understanding them as fundamental building blocks of the galactic ecosystem, marks a pivotal moment in astronomy. It means that the complex gravitational dances we've been exploring are not just sideshows, they are the main event for a huge portion of the stars in the sky. The violent ejections, the sculpted debris disks, the planets in precarious orbits, these are not rare catastrophes but common chapters in the life story of a typical star system. Our own solar system's peaceful existence begins to look less like the standard model and more like a quiet, sheltered backwater, a fortunate haven of stability in a galaxy that predominantly thrives on chaotic, multi-stellar energy. But this grand realization about the commonality of triple systems invites us to look closer to home, to our very own stellar backyard, where a profound example has been hiding in plain sight. For generations, we looked at the bright stars of the constellation Centaurus and saw a brilliant binary pair, Alpha Centauri A and B, with a faint, unrelated red dwarf floating nearby. It seemed like a simple cosmic coincidence. Then, in the early 20th century, a stunning truth emerged. That faint red dwarf, Proxima Centauri, the closest known star to our Sun, is not a lonely wanderer. It is the third, distant member of the Alpha Centauri system, making our nearest stellar neighbor a spectacular triple star system. And the orbit it follows is not a simple, gentle circle, but a wildly eccentric path that tells a story of a violent and dynamic past. Proxima Centauri's journey around the central binary is one of cosmic extremes. Its orbit is not a neat circle but a highly elongated ellipse, taking approximately 550,000 Earth years to complete a single revolution. For the vast majority of that immense timescale, Proxima maintains a respectful distance, orbiting as far as 13,000 astronomical units from the binary pair, a distance where 1 astronomical unit is the span from the Earth to the Sun. But at its closest approach, its periastron, Proxima swings in to within about 4,300 astronomical units. This means its distance from the gravitational heart of the system varies by a factor of 3, creating a rhythmic cycle of gravitational influence that has profound consequences. This eccentric orbit is a glaring clue pointing to a turbulent origin story. The most compelling theory suggests that Proxima Centauri was not born alongside Alpha Centauri A and B. Instead, it likely formed elsewhere, perhaps within the same vast stellar nursery, and was later captured by the binary's powerful gravity. This capture event would not have been gentle. It would have involved a complex gravitational interaction, possibly with other now ejected stars, that robbed Proxima of enough energy to become gravitationally bound, but left it in this strained, highly elliptical orbit. The system we see today is a fossil record of that ancient celestial billiards game, a snapshot of a dynamic process that is constantly reshaping star systems across the galaxy. The implications of this gravitational dance fall directly upon the most Earth-like world we know of beyond our solar system, Proxima Centauri b. This rocky planet, discovered in 2016, orbits within Proxima's habitable zone, the region where temperatures could allow for liquid water to exist on its surface. But the habitability of this promising world is profoundly complicated by its star's membership in a triple system. During Proxima's close approaches to the Alpha Centauri binary, the gravitational perturbations would have been significantly stronger. These repeated gravitational shocks, occurring every 500,000 years, could have violently disrupted the disk of material from which Proxima Centauri b formed, stirring up planetesimals and triggering a period of intense bombardment that would have sterilized the young planet's surface repeatedly. Furthermore, Proxima Centauri is a notorious flare star. Its magnetic activity is intense, and it frequently unleashes massive bursts of radiation that would bathe any nearby planet in deadly X-rays and ultraviolet light. The gravitational tugs from Alpha Centauri A and B, especially during close encounters, could be stirring Proxima's interior, enhancing its magnetic dynamo and making these life-threatening flares even more frequent and powerful than they would be if the star were solitary. A planet in the habitable zone of such an active star is like living next to a volcano that is constantly being shaken by earthquakes. The potential for a stable, life-friendly environment is severely challenged. This forces us to reconsider what habitability truly means. A planet like Proxima Centauri b exists not in isolation, but within the extended gravitational field of a massive binary system. Its climate and long-term stability are not governed solely by its distance from its host star. They are subject to the rhythmic pulse of external gravitational forcing, which can trigger changes in the planet's orbit, its axial tilt, and even the geological activity of its interior over astronomical timescales. The possibility of life there becomes a question of resilience. Could life arise and evolve fast enough to survive the periodic cataclysms induced by its star's eccentric dance? Or is the environment simply too chaotic, the challenges too great for biology to gain a foothold? The story of our nearest exoplanet neighbor is a testament to the fact that in a galaxy dominated by multiple stars, the path to habitability is fraught with obstacles that our own peacefully orbiting Earth never had to face. While the gravitational chaos of triple systems often leads to dramatic ejections or wildly eccentric orbits, sometimes the influence of a third star manifests in a more subtle, almost musical rhythm. This brings us to one of the most precise and beautiful phenomena discovered within these configurations, the heartbeat stars. These are not a new type of star, but rather a class of close binary stars whose dance is so exquisitely monitored by a distant third companion that they literally pulse in a rhythmic, predictable pattern like a cosmic electrocardiogram. The discovery of these systems was made possible by space telescopes like Kepler, which observed the same patch of sky for years, measuring the tiny dips in starlight with incredible precision, allowing astronomers to detect variations in brightness far more subtle than those caused by a planet's transit. The mechanism behind the heartbeat is a fascinating interplay of gravity and tidal forces. Imagine two stars similar to our own Sun, orbiting each other in a very close elliptical path. As they swing around each other, the distance between them constantly changes. When they are at their closest approach, a point called periastron, the gravitational pull of each star on the other is immense. This pull is so strong that it doesn't just affect their orbits, it actually stretches and distorts the stars themselves, much like the Moon's gravity creates tides on Earth but on a stellar scale. The stars are pulled into a slight egg shape. As they then swing apart on their elliptical journey, the tidal force relaxes and the stars spring back toward a more spherical form. This rhythmic distortion, this stretching and relaxing, causes their combined brightness to vary in a characteristic, repeating pattern that looks remarkably like a heartbeat monitor. Now introduce the third star. In a stable triple system, this distant third member exerts a steady, gentle gravitational tug on the inner binary pair as a whole. This external influence acts like a metronome, subtly altering the binary's orbit over time. It can cause the orientation of the elliptical orbit to slowly precess or rotate, and it can even cause the eccentricity of the orbit, how elliptical it is, to oscillate in a long-term cycle. These changes are reflected directly in the heartbeat signal. The timing of the pulses, their intensity, and the shape of the light curve all shift in a predictable way that is dictated by the mass and orbit of the distant perturber. The heartbeat becomes a rich data stream encoding information about all three bodies in the system. This is where the true power of heartbeat stars emerges. They function as nature's most precise celestial scales. In most binary star systems, determining the star's masses is a complex challenge that often requires making assumptions. But in a heartbeat system, the detailed analysis of the light curve provides an extraordinary amount of information. From the tidal distortions, astronomers can calculate the star's sizes and the precise shape of their orbit. The oscillations induced by the third star allow them to apply the precise mathematics of orbital dynamics to measure the mass of the perturbing object with an accuracy that is often unmatched by any other method. In essence, the inner binary acts as a sensitive probe, its rhythmic pulsing directly reporting the gravitational influence of the unseen third body. The implications of this are profound. By studying these cosmic heartbeats, astronomers can not only confirm the existence of a third star, but also determine whether it is a faint dwarf star, a white dwarf, a neutron star, or even a black hole, all based on its gravitational signature alone. This method has even been proposed as a way to detect intermediate mass black holes that might be lurking in wide orbits around binary systems. The heartbeat stars transform a seemingly chaotic triple system into a finely tuned laboratory where the fundamental properties of the stars can be measured with unprecedented precision, giving us a clearer window into stellar evolution and the intricate dynamics that govern multi-star families across the galaxy. But the precise rhythms of heartbeat stars represent just one way that triple systems can orchestrate cosmic phenomena. For a far more dramatic and violent example, we need to turn our attention to a star with a fearsome reputation, one that has been watched by humans for centuries, Algol, also known as the Demon Star. Located in the constellation Perseus, Algol is the most famous eclipsing binary in the sky. Every 2 days, 20 hours and 49 minutes like clockwork, its brightness noticeably dims for a period of about 10 hours. Ancient cultures saw this regular winking as the blink of a monstrous eye, a symbol of something sinister. We now know the simple cause, a faint, cooler star passing in front of a brighter, hotter one from our viewpoint. But Algol's true nature is far more complex and sinister than a simple eclipse. It is a triple system, and the presence of that third star is responsible for one of the most baffling and violent behaviors ever observed. For decades, astronomers understood Algol as a classic example of a mass transfer binary. The system consists of Algol A, a bright main sequence star, and Algol B, a larger but dimmer subgiant star that has evolved off the main sequence. They orbit each other so closely that their outer atmospheres are practically touching. In such a tight embrace, gravity from the more massive Algol pulls streams of gas right off the surface of its bloated companion, Algol B. This material doesn't fall directly onto Algol A, but spirals inward, forming a blazingly hot, rotating disk of accreted matter. This process is a cornerstone of stellar astrophysics, seen in everything from newborn stars to supermassive black holes. But when astronomers pointed the powerful Atacama Large Millimeter/Submillimeter Array, or ALMA, at Algol, they expected to see this stream of gas flowing neatly along the orbital plane. What they saw instead defied all expectations. The ALMA observations revealed something unprecedented. Colossal streams of carbon monoxide gas flowing between the stars, but not in the plane of their orbit. Instead, these rivers of gas were channeled along the system's magnetic field lines, shooting out from the poles of the stars. Imagine two stars whirling around each other, and instead of material flowing horizontally between them in a disk, it is being launched vertically, as if fired from cosmic cannons located at their north and south poles. This phenomenon, now termed polar streams, was completely unexpected and turned the standard model of mass transfer on its head. It suggested that magnetic forces, not just gravity, were the dominant architects of this cosmic theft. The key to this bizarre behavior lies with the system's silent third member, Algol C. This star orbits the inner, closely bound pair at a much greater distance, taking nearly 2 years to complete one revolution. While its gravitational influence is subtle compared to the fierce tug of war between Algol A and B, it acts as a long-term stabilizer. More importantly, its presence is thought to influence the dynamo processes deep within the stars, amplifying their magnetic fields to incredible strength. In a system with such complex gravitational tides and a distant perturber, the magnetic fields of Algol A and B can become tangled and enormously powerful, creating a forceful architecture that dictates the path of the stolen gas. This discovery forces a major revision of our understanding of close binary evolution. For years, the accretion disk model was considered the universal mechanism. But the polar streams of Algol demonstrate that if the magnetic field is strong enough, it can completely overwhelm the gravitational flow. The gas, being made of charged particles, becomes trapped by these magnetic highways and is funneled directly onto the star's poles at tremendous speeds. This has dramatic consequences. Matter crashing onto the magnetic poles of a star generates intense, localized hotspots of X-ray and ultraviolet radiation, turning the star into a violent, pulsating beacon of high-energy light. It also means the receiving star is being fed in a very specific, concentrated manner, which could alter its rotation, its internal structure, and its ultimate evolution in ways we are only beginning to comprehend. The implications of this extend far beyond this one demon star. Algol serves as a nearby laboratory for a process that might be occurring in countless other triple systems across the universe. Whenever you have close binary stars with a distant tertiary companion stirring the gravitational pot, the conditions might be ripe for this kind of magnetic mass transfer. This could explain unusual outbursts and energy signatures observed in other stellar systems that were previously mysteries. It suggests that the role of a third star is not always to disrupt, but sometimes to enforce a strange and powerful order, creating magnetic conduits that channel stellar material in flows of breathtaking precision and violence. The tale of Algol teaches us that even the most well-studied cosmic phenomena can harbor profound secrets, and that the invisible hand of magnetism, guided by a distant third star, can sculpt the universe in ways we are only just starting to see. This brings us to a cautionary tale from the early days of exoplanet hunting, a story that perfectly illustrates how the hidden hand of a third star can lead even the most brilliant astronomers astray. In the mid-1990s, as scientists were developing the radial velocity method to hunt for worlds beyond our solar system, they turned their telescopes toward a sun-like star called HD 188,753, located about 150 light-years away in the constellation Cygnus. The radial velocity technique is extraordinarily clever. It involves looking for the subtle wobble in a star's light. As an orbiting planet tugs on its host star with its gravity, the star moves slightly toward us and then away, causing its light to shift to the blue and then the red end of the spectrum in a repeating cycle. By measuring this wobble, astronomers can infer the presence of an unseen planet and even calculate its mass and orbital period. When researchers observed HD 188,753, they detected a clear, rhythmic signal. It pointed to the presence of a massive planet, a world roughly 1.5 times the size of Jupiter, orbiting incredibly close to the star in a mere 3.3-day orbit. It was an exciting find, a classic hot Jupiter, and it was announced to great fanfare, but there was a problem, one that would not become fully apparent for several years. Other astronomers began to take a closer look at HD 188,753 and realized it was not a single star at all. In fact, it was a tightly bound triple-star system. At its heart was a close binary pair, two stars whirling around each other in a matter of days, and this pair was itself orbited by a third star at a wider separation. The planet, if it existed, would have to be orbiting the primary star of the inner binary. This immediately threw the entire discovery into doubt. The reason lies in the violent environment of a young triple system. The standard model for how a gas giant forms, based on our own solar system, is that it begins its life in the cold, outer regions of a protoplanetary disk where there is enough ice and gas to build up a massive core. It then slowly migrates inward. However, in a system like HD 188,753, the gravitational forces from the two companion stars would have been overwhelming. Their relentless tugs would have torn apart the vast, extended disk of material needed to form a Jupiter-sized planet long before it could ever coalesce. The very existence of such a planet in that location defied everything we thought we knew about planetary formation. The mystery deepened as follow-up observations failed to conclusively confirm the planet's signal. The initial wobble seemed to vanish or become inconsistent when analyzed with more sophisticated tools that accounted for the complex motions of all three stars. What astronomers eventually concluded was a stunning revelation. The wobble they had attributed to a planet was most likely not caused by a planet at all. Instead, it was a subtle artifact, a ghost in the machine created by the intricate gravitational dance of the three stars themselves. The complex orbital motions and the tidal forces they exerted on each other were distorting the stars' surfaces and their light in ways that mimicked the precise, repeating signal of an orbiting planet. The third star, once thought to be a mere bystander, was actually the key player, its gravitational influence generating a false positive that had tricked the detection methods of the time. This discovery had a profound and immediate impact on the field of exoplanet science. It served as a critical wake-up call, highlighting a major pitfall in the hunt for new worlds. It forced astronomers to become far more rigorous in their vetting process. Before claiming a planet detection around any star, they now had to answer a fundamental question with absolute certainty: is this star truly alone? The presence of an unresolved stellar companion, whether a close binary or a wide tertiary star like in HD 188,753, could easily contaminate the data. This led to the development of new observational techniques, such as using adaptive optics to directly image the star system to search for faint companions that might otherwise be lost in the glare. It taught the community that the universe is full of gravitational echoes, and that what looks like the whisper of a planet might sometimes be the distant rumble of another sun. The legacy of the HD 188,753 non-planet is therefore not one of failure but of scientific progress. It sharpened our tools and deepened our understanding of stellar dynamics. It reminded us that triple star systems are not just exotic curiosities. They are complex environments whose physics can confound our initial interpretations. Every false positive like this one forces us to refine our models and improve our technology, making subsequent discoveries all the more robust. The next time you hear about a newly discovered exoplanet, you can be confident that the team behind the discovery has, in part thanks to lessons learned from HD 188,753, done the painstaking work to rule out the possibility that they are simply seeing the hidden gravitational signature of a stellar sibling. The quest to understand these cosmic families has led astronomers to some of the most peculiar stellar characters in the galaxy, and few are more enigmatic than the so-called blue stragglers. Picture a crowded star cluster, an ancient city of suns where every star was born at roughly the same time from the same giant cloud of gas and dust. As these stars age together, they follow a predictable path. The massive, bright blue stars burn through their fuel quickly and die young, while the smaller, redder stars live for trillions of years. If you were to map this cluster, you would see a clear evolutionary sequence, a main sequence, with a distinct turn-off point where the massive stars have already departed. But scattered among the older, redder population, you occasionally find a few stars that break all the rules, stars that are blazingly hot, blue, and massive, shining defiantly as if they were still in their youth. These are the blue stragglers, the rebellious teenagers who crashed the senior citizens' home, and their very existence is a paradox that demands an explanation. For a long time, the origin of these youthful-looking stars in ancient environments was a profound mystery. How could a star appear billions of years younger than its neighbors? The leading theory points to a process of stellar rejuvenation, a cosmic fountain of youth that requires a dramatic intervention. One of the most compelling mechanisms involves a violent stellar merger. In a densely packed star cluster or within a tight multiple star system, two older, lower mass stars can be gravitationally forced into a collision course. Imagine two suns, perhaps similar to our own, that have been dancing a dangerously close tango for eons. Their gravitational interaction slowly drains energy from their orbit, drawing them ever closer until their outer atmospheres touch. What follows is not a catastrophic explosion, but a relatively gentle merging. The two stars spiral into each other, their material mixing to form a single new star. This newly formed star is fundamentally different from its progenitors. It has a larger mass and a fresh supply of hydrogen fuel dumped into its core, reigniting nuclear fusion with a new intensity. The result is a star that is hotter, bluer, and more luminous than either of its parent stars had been for billions of years. It effectively hits the reset button on its life, appearing as a straggler that has fallen behind the main evolutionary sequence of the cluster. But for this merger to happen, the two stars need a catalyst, a way to lose the orbital energy that keeps them apart. This is where the architecture of a triple star system becomes the perfect staging ground for this cosmic rebirth. In a stable triple configuration, the gravitational influence of the third star acts as a subtle but persistent architect of chaos. Through a process known as the Kozai-Lidov mechanism, the distant third star can periodically torque the inner binary pair, driving their orbit to become highly eccentric. Over thousands of cycles, the eccentricity can grow so extreme that at their closest approach, the two stars nearly graze each other. This dramatically increases tidal forces, which in turn dissipates orbital energy, causing the stars to spiral inward. The presence of the third star provides the gravitational nudge necessary to push a stable binary system over the edge into a merging embrace. After the merger is complete, what remains is a single, rejuvenated blue straggler star, now orbiting peacefully with the third star that orchestrated its creation. This brings us back to the system of HD 188,753, the same triple system that once fooled astronomers with a phantom planet. While the hot Jupiter discovery may have been an illusion, the system itself is very real and serves as a compelling candidate for hosting this very process. The inner pair of HD 188,753 consists of two stars locked in a tight orbit. The gravitational perturbations from the wider orbiting third star could have, over the system's long history, induced the kind of orbital decay that leads to stellar mergers. It is entirely plausible that one of the stars we see today in that inner binary is not a primordial star, but a blue straggler, the product of an ancient merger that was choreographed by the tertiary companion. While confirming this directly is challenging, the dynamics of the system are perfectly suited for it, turning HD 188,753 from a cautionary tale into a potential example of stellar evolution in action. The discovery of blue stragglers in triple systems fundamentally changes our view of stellar life cycles. It demonstrates that a star's fate is not always a solitary journey from birth to death. In the crowded gravitational landscapes of multiple star systems, destinies can intertwine and merge, creating entirely new stellar entities that defy simple age classification. This process also has profound implications for the chemical enrichment of galaxies. The merger of two stars can expose previously hidden layers of nuclear processed material, scattering new elements into space and altering the chemical makeup of future generations of stars and planets. The blue straggler, born from a violent dance of gravity, is a testament to the dynamic and interconnected nature of the cosmos. where even the life story of a star can be rewritten by the pull of its companions. But the violent mergers that create blue stragglers are merely a prelude to an even more extreme and fundamental consequence of stellar interaction. The same gravitational dynamics that confuse two ordinary stars can also orchestrate collisions on a far more massive and invisible scale, events that do not just create new stars but shake the very fabric of the universe. This brings us to the role of tight triple systems as gravitational wave factories. Gravitational waves are the ripples in space-time predicted by Einstein's theory of general relativity, literal distortions in the cosmic landscape caused by the acceleration of massive objects. For decades, they were merely a theoretical concept, but in 2015, the LIGO Observatory made history by directly detecting these waves for the first time, originating from the collision of two black holes over 1 billion light-years away. The question immediately arose, how do black holes get close enough to merge? The answer for many of these events points directly to the chaotic environments of triple star systems. To understand why triples are so effective at producing these cosmic tremors, we need to consider the fate of the most massive stars. In a dense stellar environment, it's not uncommon for three very massive stars to be born together in a tight gravitational embrace. These stars live fast and die young, exploding as supernova and leaving behind ultra-dense corpses, either neutron stars or black holes. If the original triple system survives these violent deaths without being torn apart by the explosive kicks, you are left with a triple system of compact objects. This is where the real gravitational dance begins. The interactions between these three incredibly dense remnants are fierce and complex. The Kozyledov mechanism, which we saw can drive stellar mergers, becomes exceptionally powerful here. The gravitational perturbations from the outer object can pump the eccentricity of the inner binary of neutron stars or black holes to extreme levels. This process effectively short-circuits the natural, slow orbital decay that would take billions of years. Instead of a gradual spiral, the inner binary is driven into a highly elliptical orbit where the objects whip around each other, coming extraordinarily close at periastron. During these close encounters, an enormous amount of energy is lost not through friction, but through the emission of gravitational waves themselves. Each close pass radiates energy away, shrinking the orbit and making it more circular. This creates a runaway feedback loop. The closer they get, the more gravitational waves they emit, and the more waves they emit, the closer they get. This can accelerate a merger timeline from timescales longer than the age of the universe down to just a few million years, making triple systems incredibly efficient factories for producing catastrophic collisions. The data from LIGO and its European counterpart, Virgo, is beginning to reveal signatures that point to this triple origin story. One key clue is the spin of the merging black holes. If two black holes form together from a binary star system and evolve in isolation, their spins are often expected to be aligned with their orbital axis. However, if a third object is constantly perturbing the system, it can tilt and misalign those spins in a chaotic fashion. Several of the black hole mergers detected by LIGO show evidence of misaligned spins, a tantalizing hint that a third party was involved in choreographing the final dance. Furthermore, the very high masses of some of the detected black holes suggest they themselves might be the product of previous mergers within a hierarchical triple system, where a black hole that merged with a companion is then pushed into a second merger by the persistent gravitational influence of the third object. The implications of this are profound. If a significant portion of the gravitational wave events we detect are born in triple systems, it means that these chaotic stellar families are not just minor players in the cosmos. They are primary engines for some of the most energetic events since the Big Bang. The merger of two neutron stars, for instance, is not only a source of gravitational waves, but also the cosmic forge where heavy elements like gold, platinum, and uranium are created and scattered into the galaxy. The gold in a wedding ring or the uranium in a power plant was likely born in the fiery collision of two dead stars, a collision that may have been orchestrated by the gravitational nudges of a long-vanished third star. By studying the statistics of gravitational wave events, astronomers can essentially take a census of the dynamics within these dense stellar environments, piecing together the life stories of stars that died long ago. Each ripple in spacetime is a final message, a testament to a dramatic history of gravitational interplay that began with 3 stars and ended with a universe-shaking crash. While the spectacular collisions of black holes represent the cosmic endgame for some triple systems, the story of their influence begins at the very moment of their birth, within the swirling, dusty nurseries where stars first ignite. It is in these young stellar environments that we find the key to 2 interconnected mysteries: the strange abundance of free-floating, planet-like objects drifting alone in the darkness, and the bizarre, warped shapes of the disks where future planets are struggling to form. The chaotic nature of triple stars is not just a feature of their old age. It is a fundamental characteristic imprinted upon them from their very first breaths. The process of star formation is a turbulent affair. A vast cloud of gas and dust collapses under its own gravity, fragmenting into smaller clumps that will become individual stars. Sometimes a single clump itself can fragment further, giving birth to 2, 3, or even more stars in a tight-knit group. These newborn stellar siblings are initially bound together, but their gravitational relationship is often precarious from the start. In a significant number of these young triples, the system is inherently unstable. The stars, still settling into their orbits, engage in a frantic gravitational tug-of-war. Through a series of close encounters, energy is transferred between them, and almost always, the star with the least mass, the weakest gravitational player, is the one that loses out. It can be slingshotted away from its siblings at high speed, condemned to a lonely existence as a runaway star. This rapid ejection, occurring just a few million years after the stars are born, solves a long-standing puzzle in astronomy: the origin of free-floating planetary mass objects. For years, telescopes like the James Webb Space Telescope have been spotting faint, warm objects adrift in star-forming regions like the Orion Nebula. These objects are too small to be stars. They lack the mass to ignite fusion in their cores, yet they do not orbit any sun. They are often referred to as rogue planets or Jupiter mass binary objects. But how did they form? The traditional model of planet formation requires a disk around a young star. The discovery that young triple systems frequently eject their smallest member provides a compelling alternative. The ejected body isn't necessarily a planet that formed in a disk and was later flung out. It could be a failed star, a brown dwarf that was born alongside its more massive siblings and violently evicted from its home before it could settle into a stable orbit. This means many of these lonely worlds may not be planets at all, but rather the smallest products of the star formation process itself, orphans created by the gravitational chaos of their turbulent birth families. The gravitational turmoil of a young triple system leaves its mark not only on the stars but also on the material left over from their formation, the protoplanetary disks. These vast, rotating pancakes of gas and dust are the cradles of planets, the regions where dust grains stick together to eventually form asteroids, comets, and entire worlds. In a calm, single-star system like our early solar system, this disk is typically flat and orderly, like a vinyl record spinning around the central star. But when you place a young star with its disk into a multiple star system, the gravity of the companion stars acts as a powerful sculptor, warping and twisting the disk into incredible shapes that defy simple geometry. Astronomers using the Atacama Large Millimeter/Submillimeter Array have observed these distorted disks around young triple stars, and the images are breathtaking. Instead of a single, flat plane, the disks can appear bent like a warped phonograph record, or they can be broken into distinct, misaligned rings that look like a celestial hula hoop. In one remarkable system, a triple star named GW Orionis, the disk has been pulled into a spectacularly tilted inner ring, completely disconnected from the outer disk, with shadows and gaps suggesting the complex gravitational forces are already carving paths and triggering planet formation in these strained environments. The gravity of the stellar companions constantly torques the disk, generating friction and heat, and potentially accelerating the growth of planetesimals by forcing dust and pebbles into dense, collision-prone regions. This dynamic has a double-edged consequence for planet formation. On one hand, the severe gravitational perturbations can be destructive. They can truncate the disk, stripping away its outer material and limiting the amount of raw matter available to build planets. They can also stir up the disk, increasing the relative speeds of colliding particles so that they shatter upon impact rather than gently sticking together. This could stifle the very first steps of planet birth. On the other hand, this same chaos might also be creative. The warps and twists can act as pressure traps, concentrating solid material into narrow, dense bands that are ideal for the rapid formation of planetary cores. It might even be possible for planets to form on highly inclined or even retrograde orbits, completely opposite to the spin of their host star, something that would be nearly impossible in an isolated system. The warped disks around young triples show us that the birthplace of planets is not always a quiet, orderly nursery. It can be a chaotic construction site where the gravitational blueprint is constantly being redrawn by the unruly siblings dancing nearby. Moving from the gravitational turmoil of stellar nurseries, we encounter a trio of discoveries that showcase the sheer diversity of outcomes within triple systems, from the birth of the most magnetic objects in the universe to the enduring stability that allows for the chemistry of life to begin. Our first oddity takes us to the extreme end of stellar evolution, to a system harboring a magnetar. Magnetars are a rare and terrifying type of neutron star, the collapsed core of a giant star that went supernova. What sets them apart is an almost unimaginably powerful magnetic field, trillions of times stronger than Earth's and even dwarfing that of a typical neutron star. The magnetic field around a magnetar is so intense that it can crack the star's solid crust, releasing colossal bursts of gamma rays and X-rays in what are known as starquakes. For a long time, how a star could produce such an extreme magnetic field was a major puzzle, and the answer may lie in the dramatic dynamics of a triple system. The leading theory suggests that a magnetar is the product of a stellar merger, a cosmic event perfectly set up by a triple star configuration. Imagine a massive, close binary system where both stars are destined to become neutron stars. Their evolution is swift and violent. The more massive star explodes first, leaving behind a neutron star. As its companion star ages and begins to swell into a red giant, it can transfer a huge amount of mass onto the neutron star companion. This rapid infusion of matter spins the neutron star up to incredible rotation speeds, acting like a powerful dynamo that amplifies its magnetic field to magnetar levels. But to make this process efficient enough, the binary needs to be very close, and that's where the third star comes in. A distant tertiary companion can, through the Kozylidov mechanism, drive the inner binary's eccentricity to such extremes that the stars interact and merge, or come so close that the mass transfer is exceptionally violent and rapid. This stellar tango, choreographed by a third partner, provides the ideal conditions for forging a magnetar, turning a triple system into a factory for some of the most magnetically hostile objects in the cosmos. In stark contrast to the violent origins of a magnetar, our next discovery reveals a triple system that is a paragon of cosmic peace and longevity. This is the story of a perfectly hierarchical system, a gravitational architecture that is the key to survival in the multi-stellar world. In a hierarchical triple, you have two stars locked in a tight, close orbit, and this pair is then circled by a third star at a much greater distance. The wide separation between the inner binary and the outer star minimizes gravitational interference, creating a stable configuration that can persist for billions of years, essentially for the entire lifetime of the stars. It's a stellar family that has found a way to live together in harmony, a testament to the fact that not all triple systems are doomed to chaos. We see this beautiful stability in systems like Alpha Centauri itself, but also in many older triple systems found in globular clusters, some of which are nearly as old as the universe itself. Their endurance tells a profound story about orbital dynamics. The stability arises from a clear separation of scales. The outer star's gentle gravitational influence acts on the inner binary as a single unit, rather than trying to pull the individual stars apart. This allows planets to potentially form in stable orbits around one or more of the stars, offering a haven for worlds in an otherwise tumultuous galactic environment. The existence of these ancient, stable triples demonstrates that multiple star systems are not just temporary, chaotic arrangements, but can be enduring features of the galaxy, providing stable environments over cosmological timescales where the slower processes of planetary evolution and even the development of life could, in theory, take place. Perhaps the most inspiring discovery of this trio comes from the study of young triple systems, where astronomers have made a finding that blurs the line between chaos and creation. Using powerful radio telescopes, scientists have peered into the protoplanetary disks swirling around young stellar triples and detected the spectral signatures of complex organic molecules. These are not simple compounds like water or carbon monoxide, but more advanced molecules like acetic acid, the main component of vinegar, and even glycine, a fundamental amino acid that is a building block of protein. The presence of these molecules in such a dynamically stressed environment is astounding. It suggests that the basic chemical prerequisites for life can emerge even within the gravitational whirlwind of a triple star system. This discovery challenges the notion that planet formation needs a quiet, serene environment to produce the ingredients for biology. The warped and heated disks around young triples might, in fact, accelerate certain chemical processes. The gravitational perturbations that twist the disks could create localized hotspots of density and temperature, acting as cosmic pressure cookers where simple molecules are forced together, facilitating the reactions that lead to more complex organics. While the long-term stability of a planet in such a system remains a question, the fact that the chemistry can begin at all is a revolutionary idea. It means that the building blocks of life are not fragile, rare commodities, but robust and widespread, capable of forming in some of the most chaotic and energetic nurseries the galaxy has to offer. The path from stardust to the precursors of life appears to be a resilient one, able to commence its work under the light of 3 suns just as readily as under one. The violent ejections we see in young triple systems are not just a local phenomenon. They can operate on a galactic scale, producing some of the fastest-moving objects in the entire Milky Way. These are the hypervelocity stars, stellar projectiles rocketing through space at speeds so great they can completely escape the gravitational pull of our galaxy. For a long time, the origin of these cosmic speedsters was a mystery, with theories pointing to interactions with the supermassive black hole at the galactic center. But we now understand that the dramatic disintegration of a tight triple star system is a powerful engine for launching these runaways. The mechanism is a gravitational slingshot of breathtaking efficiency. In an unstable triple, the complex dance can transfer an enormous amount of orbital energy to the lowest mass star. This is not a gentle nudge, it is a catastrophic expulsion, accelerating the star to velocities exceeding 1,000 kilometers per second, fast enough to cross the entire United States in less than 5 seconds. Tracing these stars back to their point of origin is a forensic challenge that reveals the hidden history of our galaxy's stellar neighborhoods. Astronomers use precise measurements of a runaway star's velocity and direction, its kinematics, to rewind its trajectory through the Milky Way. By factoring in the gravitational pulls of stars, gas clouds, and the galaxy's dark matter halo over millions of years, they can project its path backwards in time. This cosmic backtracking often leads not to a solitary point, but to a specific region, like a dense star cluster or a known binary system. When we find a binary in the suspected birthplace and the kinematics of the runaway star perfectly align, it provides compelling evidence that the system was once a triple. The runaway is the missing piece, the ejected third member whose sudden departure left the remaining binary in a stable but altered state. This process does more than just create stellar orphans. It dynamically heats the galaxy's stellar population, injecting high-speed stars into the halo and effectively redistributing stellar mass on a grand scale. While the ejection of a single star is a dramatic event, it pales in comparison to the ultimate cosmic showdown that can occur when triple systems involve the most massive objects in the universe, supermassive black holes. At the heart of most large galaxies, including our own Milky Way, lies a supermassive black hole weighing millions or even billions of times the mass of our Sun. Galaxies are not static islands, they collide and merge over cosmic time. When two galaxies merge, their central black holes are drawn together by gravity, eventually forming a binary pair. But what happens if both merging galaxies already have a binary black hole system at their core? The result of this colossal collision could be a triple supermassive black hole system, a configuration of almost unimaginable gravitational power. The dynamics within such a system are a supercharged version of the stellar mass triple interactions we've seen, but with consequences that ripple across the cosmos. The three black holes would engage in a ferocious gravitational dance, inevitably leading to the ejection of the lightest of the three. However, before that ejection occurs, their interactions would be a primary source of the low-frequency gravitational waves that future space-based observatories like LISA are designed to detect. The merger of any two of these giants would produce a gravitational wave burst of staggering amplitude, a transient signal that would stand out against the continuous hum of the universe. This burst would carry unique signatures, potentially showing a sudden termination or a rapid frequency shift if the third black hole is ejected during the final moments of the merger, a fingerprint of the triple's chaotic final act. The search for these triple titans is actively underway, with astronomers scanning the centers of merging galaxies for telltale signs. One promising method involves looking for quasars, extremely bright galactic cores powered by accreting supermassive black holes that show periodic variations in their brightness. These variations could be caused by a third black hole perturbing the accretion disk of an inner binary, creating a regular pattern of outbursts. Finding even one confirmed triple supermassive black hole system would have profound implications. It would provide direct evidence for a key pathway through which black holes grow to such immense sizes, through a series of galactic mergers and subsequent black hole mergers. It would also confirm that the centers of galaxies are even more dynamically violent and complex than we currently imagine, hosting gravitational interactions that shape the evolution of the entire galaxy itself. The potential detection of the gravitational waves from such a system would open a new window into the most energetic events since the Big Bang, allowing us to witness the final moments in the life of a triple system that began with the collision of entire galaxies. The existence of planets in these chaotic environments leads us to one of the most mind-bending concepts in all of astronomy, the circumtriple planet. Imagine a world that doesn't orbit just one star or even a close binary pair, but all three stars at once. This isn't a planet nestled within the inner gravitational turmoil. Instead, it would hold a distant, majestic orbit so vast that it encircles the entire triple system, treating the three dancing suns as a single gravitational point at its center. The orbit of such a world would be unlike anything in our solar system. It wouldn't be a simple, near-circular path. The combined shifting gravity of the three central stars would pull the planet into a complex precessing ellipse, a grand, slow-motion loop that might look like a gently spinning spirograph pattern on a scale of thousands of astronomical units. A single year on this world could span many thousands or even tens of thousands of Earth years, with seasons lasting for millennia. The view from its surface, however, would be a spectacle beyond compare. Three suns of possibly different colors and brightnesses tracing intricate celestial patterns against a perpetual twilight sky. While a circumtriple planet enjoys a grand, stable view from afar, the story for planet formation closer to the stellar tumult is one of both destruction and opportunity. The inner regions of a young triple system are a gravitational war zone. The constant tugging from the multiple stars creates powerful resonances and shear forces that prevent the delicate process of planet formation from ever getting started. Dust grains and pebbles that would gently stick together in a quiet disk around a single star are here stirred to such high velocities that they shatter upon collision instead of accreting. This effectively sterilizes the inner system, creating a vast zone where planets cannot form. Yet, this same chaotic stirring has a creative consequence much farther out. The gravitational interactions act like a cosmic paddle, churning the outer protoplanetary disk and forcing solid material like water ice, methane, and other volatiles into dense, concentrated rings. This process pushes the system's frost line, the distance from the stars where volatile materials can condense into solid ice, to a much greater radius than in our own solar system. This outward shift of the frost line is a game changer for planetary formation. In our system, the frost line sits roughly in the asteroid belt between Mars and Jupiter, which is why the inner planets are rocky and the outer planets are gas and ice giants. They formed beyond the line where there was an abundance of icy material to build massive cores. In a triple system, this critical boundary could be pushed out to a distance equivalent to Pluto's orbit or even farther. This means that the prime real estate for forming giant planets is not in the cozy inner regions, but in the deep freeze of the outer system. It suggests that if a triple system like this manages to form planets, they are more likely to be ice giants or gas giants orbiting at tremendous distances, with any potential terrestrial worlds being rare outliers that somehow manage to coalesce against all odds in the gravitationally hostile inner zone. This brings us to the ultimate question: could such a system host a habitable world? The possibility, while challenging, is not zero. The most plausible scenario involves a wide, hierarchical triple system, like a scaled-up version of Alpha Centauri. In this configuration, a potentially habitable planet would orbit the largest, most stable star in the system, let's call it Star A, at a distance that places it squarely within that star's traditional habitable zone. The other two stars, B and C, would form a tight binary pair orbiting each other at a much greater distance from Star A and its planet. From the planet's perspective, Star A would be its primary sun, providing the bulk of the heat and light necessary for liquid water. The binary pair, however, would appear as extraordinarily brilliant stars in the sky, far outshining anything we see from Earth. The day and night cycles on this world would be bizarre and beautiful. During its day, the primary sun, Star A, would dominate the sky, but as it set, the binary pair of stars B and C might rise, casting a soft, compounded glow that could create a perpetual twilight or even a second, fainter daytime. There would be periods when all three suns are above the horizon, and other times when the planet experiences a true, deep night if all three have set. The light from the binary would not provide significant warmth compared to the primary star, but it would be a constant, dramatic presence, illuminating the landscape with an eerie, multi-source light that casts multiple, faint shadows. The true challenge for life would be long-term climate stability. The gravitational influence of the distant binary, while weak, would act over millennia, potentially causing subtle changes in the planet's orbit or axial tilt. These Milankovitch-like cycles, but amplified by the presence of multiple gravitational perturbers, could trigger ice ages or warming periods on geological timescales, presenting a formidable hurdle for the evolution of complex life. Yet, the mere possibility that such a world could exist expands our concept of a habitable environment from a single, tranquil star to the complex and dynamic sphere of influence within a multi-star family. But the gravitational choreography that shapes planetary orbits and stellar mergers can also fuel a far more intimate and sinister form of stellar interaction. This brings us to a pair of discoveries that showcase the dramatic life and death struggles happening within these systems, from a process of cosmic vampirism to the creation of the universe's most precise timepieces. In the tight gravitational embrace of a close binary star system, a celestial drama can unfold where one star acts as a vampire, slowly draining the lifeblood from its companion. This process, known as mass transfer, is dramatic enough on its own, but within a triple system, it can be triggered and intensified by the ever-present influence of the third star. Imagine two stars born together, one slightly more massive than the other. The more massive star lives a faster, more extravagant life, burning through its hydrogen fuel and evolving into a red giant, swelling to hundreds of times its original size. If its companion is close enough, the outer layers of this bloated giant can be gravitationally captured by the smaller, denser star. The material doesn't just fall directly, it spirals in, forming a hot, bright disk of accretion around the vampire star. This stolen material reinvigorates the recipient, making it hotter, brighter, and spinning it up to tremendous speeds. Meanwhile, the donor star is left as a stripped-down, exposed core, a faint and dying ember. This process can completely transform the appearance and evolution of both stars, creating a bizarre pairing that defies their original destinies. The role of the third star in this drama is that of a subtle puppeteer. Its gravitational nudges, operating on long timescales through mechanisms like Kozai-Lidov, can perturb the inner binary's orbit. It can make their path more elliptical, driving the stars to pass perilously close to each other at periastron, dramatically enhancing the tidal forces that strip material from the larger star. In this way, the distant third star can be the catalyst that initiates the vampiric feeding frenzy, turning a stable binary into a system of stellar cannibalism. For an example of this, we need look no further than the system of Algol, which we discussed earlier. While its polar mass streams are a unique magnetic phenomenon, the underlying driver is still this vampiric relationship. The subgiant Algol B is actively being drained of its outer layers by its more massive companion, Algol A, a process that was likely initiated and is now maintained by the gravitational influence of the third star, Algol C. This system stands as a stark reminder that the peaceful hierarchy of a triple system can mask a violent struggle for survival happening in its heart. If stellar vampirism represents one extreme of stellar interaction, then the discovery of pulsars within triple systems offers a glimpse into the opposite end of the spectrum, unimaginable precision born from stellar death. A pulsar is a type of neutron star, the ultra-dense, city-sized corpse of a massive star that went supernova. What makes a pulsar special is its rapid rotation and incredibly strong magnetic field, which are misaligned. This combination acts like a cosmic lighthouse, beaming out intense radiation from its magnetic poles. As the star spins, this beam sweeps across space, and if it points toward Earth, we detect a regular pulse of energy with a timing so exact it rivals atomic clocks. When such a pulsar is found in a triple system, it becomes one of the most powerful tools in all of astrophysics. The timing of its pulses is exquisitely sensitive to any motion of the pulsar itself. If the pulsar is orbiting other objects, the precise rhythm of its ticks will be slightly advanced or delayed as it moves toward and away from us. By minutely analyzing these tiny variations in the pulse arrival times, astronomers can map the entire orbital dance of the system with breathtaking accuracy. This technique, known as pulsar timing, allows for the detection of the pulsar's companions, even if they are themselves dark and invisible, like other neutron stars or black holes. Perhaps the most famous example is the PSR J0337 1715 system, discovered in 2012. This remarkable system contains a millisecond pulsar, spinning hundreds of times per second, orbited by two white dwarfs in a complex hierarchical arrangement. The pulsar timing measurements are so precise that astronomers can not only determine the masses of all three stars with unparalleled accuracy, but also test the very foundations of gravity itself. They can see if the gravitational influence of the outer white dwarf on the inner pair is exactly as predicted by Einstein's theory of general relativity, even in this strong field regime. Any deviation from the predictions could point toward new physics. The pulsar in this triple system acts as a probe, its unwavering ticks revealing the gravitational landscape it moves through, turning a cosmic graveyard into a pristine laboratory for fundamental physics. The contrast is striking, from the chaotic, life-draining act of stellar vampirism to the creation of a natural timepiece of such perfection that it allows us to test the laws of the universe itself. The challenge of studying a triple star system begins with a seemingly simple problem. How do you separate the combined light of three suns into its individual components? This is where the power of spectroscopy transforms from a tool into a form of cosmic forensic science. When we point a telescope at a distant triple system, we typically see just one point of light. But by passing that light through a spectrograph, we can spread it out into a rainbow, revealing a rich tapestry of dark and bright lines known as a spectrum. Each element in a star's atmosphere leaves a unique fingerprint, a specific pattern of lines. In a single star, these lines are sharp and clear, but in a triple system, the spectrum becomes a complex superposition of three sets of fingerprints, all shifted and blended together. The stars, as they orbit each other, are constantly moving relative to us. This motion causes their spectral lines to shift back and forth due to the Doppler effect, much like the changing pitch of a siren as it passes by. Advanced computational techniques allow astronomers to disentangle this mess. By taking hundreds of spectra over time and feeding the data into sophisticated models, they can essentially deconstruct the blended light. The computer tests millions of possible configurations, different combinations of stellar masses, orbital speeds, and temperatures until it finds the one that perfectly reproduces the observed wobbling and blending of the spectral lines. The result is nothing short of miraculous. From a single point of light, we can extract the individual temperatures, masses, chemical compositions, and even the approximate ages of all three stars. We learn that one star is a hot, blue, massive giant, another is a sun-like yellow dwarf, and the third is a cool, diminutive red dwarf. This spectral dissection reveals the complete character of each stellar actor in the dance, providing the fundamental data needed to understand the system's history and future. This powerful analytical technique allows us to look far back in time, to some of the very first generations of stars that formed in our galaxy. In the sparse, ancient halo that surrounds the Milky Way's bright disk, astronomers have identified triple star systems that are truly cosmic fossils over 12 billion years old. These systems are relics from an era when the universe was young, filled only with hydrogen, helium, and trace amounts of lithium, the pristine elements forged in the Big Bang. The stars in these triples are metal-poor, meaning they contain very few of the heavier elements that are abundant in stars like our Sun. Their existence is a profound puzzle. Our current models suggest that in the early universe, the gas clouds were warmer and less prone to fragmentation, making it harder to form multiple stars from a single collapse. Finding ancient triples forces us to reconsider those conditions, indicating that the process of stellar multiplicity began almost as soon as the first stars ignited. These senior stellar systems act as time capsules, Their chemical composition is a direct record of the interstellar medium from which they condensed. By studying their spectra, we confirm that the early universe was indeed a simpler place, chemically speaking, but their very architecture, their stable, hierarchical orbits that have persisted for billions of years, tells us something even more fundamental. It demonstrates that the gravitational physics governing multiple star systems has been in operation and effective since the dawn of the galaxy. The survival of these fragile triples through eons of galactic mergers and close encounters with other stars suggests they formed in relative isolation and have led remarkably peaceful lives, offering a quiet window into the infancy of cosmic structure. Yet for every ancient, stable system, there are many more that bear the scars of a violent birth. One of the most telling pieces of evidence is the common discovery that the orbital planes within a triple are often wildly misaligned. In a simple, clean formation model, you might expect all three stars to form from a single, flat, rotating disk of gas, much like planets around a star. In this scenario, the orbits of all the stars should lie in the same plane, but observations consistently show that this is frequently not the case. The orbit of the distant third star is often tilted, sometimes dramatically, relative to the plane of the inner binary pair. This misalignment can be anything from a slight inclination to a perpendicular orbit, or even a retrograde orbit where the outer star moves in the opposite direction to the inner binary. This misalignment is a glaring signature of a turbulent origin. It strongly suggests that the three stars did not form together peacefully from a single disk. Instead, the most likely explanation is that the stars formed in separate, smaller groupings within a dense, chaotic stellar nursery. As these young stars drifted through their birth cloud, a close gravitational encounter brought them together. One star, perhaps originally part of a binary, was captured by another binary, forging a new triple system. Because this capture is a chaotic, three-dimensional event, the resulting orbits are rarely neatly aligned. The gravitational interplay during this chaotic meeting can leave the outer star orbiting in a completely different plane, a permanent monument to the frenzied environment of its birth. This finding shatters the idea of serene stellar nurseries, painting a picture instead of a dynamic, crowded region where young stars jostle and gravitationally bully each other, with triple systems being one of the most dramatic outcomes of this celestial scattering. From the precise ticks of a pulsar's clock to the violent rebirth of a blue straggler, we've seen how a third star can orchestrate both order and chaos. But perhaps nowhere is its influence more dramatically destructive than in a class of systems known as cataclysmic variables. These are stellar partnerships defined by their volatility, consisting of a white dwarf, the Earth-sized core of a dead star, locked in a tight, frantic dance with a living companion, typically a main sequence star like our Sun. The white dwarf's immense gravity relentlessly pulls hydrogen-rich gas from its victim, channeling this stolen material onto its own scorching hot surface. For a time, this process simmers, but it inevitably leads to a thermonuclear inferno, a nova eruption that can blast the accumulated gas into space in a blinding flash. For decades, the evolution of these binaries was thought to be a straightforward two-body affair. Yet, a growing body of evidence reveals that a silent, distant third star is often the hidden director of this entire cataclysmic drama. This brings us to our 26th discovery, the role of the third star as a gravitational architect, dramatically shrinking the orbit of the inner binary and accelerating its evolution towards explosive outbursts. The key to this process is a phenomenon we've encountered before, the Kozai-Lidov mechanism. In a stable triple system, the gravitational tugs from the distant third star don't just gently perturb the inner binary, they can systematically torque its orbit. Over thousands of years, this constant nudging can pump the eccentricity of the white dwarf and its companion's orbit, making it incredibly elongated. When the two stars swing perilously close at periastron, their atmospheres nearly touch and powerful tidal forces are unleashed. These tides act as a brake, dissipating orbital energy and causing the stars to spiral inward. The presence of the third star, therefore, provides an efficient mechanism to drive the binary pair closer together than they ever could have on their own, turning a wide, stable pair into a tight, interacting cataclysmic variable in a fraction of the time. The consequences of this orbital shrinkage are profound. As the stars get closer, the gravitational grip of the white dwarf intensifies, dramatically increasing the rate of mass transfer from its donor companion. What might have been a slow trickle of gas becomes a raging river flowing onto the white dwarf's surface. This sets the stage for more frequent and potentially more powerful nova eruptions. Furthermore, a tighter orbit means the entire cycle of accretion and explosion happens on a faster clock. Systems that might have taken billions of years to become active can be thrust into their violent phase in just a few 100 million years, all because of the persistent gravitational influence of their tertiary companion. This discovery fundamentally alters our timeline for these events, suggesting that many of the cataclysmic variables we see today are not ancient relics, but systems whose violent destinies were fast-tracked by an unseen third body. For our 27th discovery, we can look at a specific system that serves as a textbook example of this process in action, a cataclysmic variable known as Z Chameleontes. This system has been studied for decades, known for its regular outbursts. However, detailed astrometric measurements from missions like Gaia have revealed a tantalizing clue, a subtle wobble in the system's motion through space that cannot be explained by the binary pair alone. The most plausible explanation is the gravitational pull of a third object, a low-mass star or even a brown dwarf, orbiting at a distance of several hundred astronomical units. While this companion is too faint to see directly, its gravitational signature is etched into the path of the inner binary. In a system like Z Chameleontes, the tertiary companion's role is thought to be absolutely critical. By driving the initial orbital shrinkage, it created the conditions for the intense mass transfer we observe today, but its influence doesn't stop there. Even now, its gravitational perturbations continue to subtly affect the binary's orbit, potentially modulating the flow of material. This can explain peculiarities in the system's outburst pattern, such as slight variations in the time between eruptions or the intensity of the explosions. The third star acts as a permanent gravitational hand on the thermostat, occasionally tweaking the settings of this cosmic pressure cooker. Z Chameleontes is likely not unique. Many other cataclysmic variables probably host unresolved tertiary companions, their presence masked by the glare of the erupting binary, but their influence felt in every aspect of the system's violent behavior. This relentless feeding frenzy, orchestrated by the third star, leads us to the ultimate and most consequential question, our 28th discovery. Could these triple systems be the primary progenitors of Type Ia supernova? A Type Ia supernova is one of the most energetic events in the universe, a titanic explosion that completely obliterates a white dwarf. These blasts are so incredibly bright and uniform that they serve as standard candles, allowing astronomers to measure vast cosmic distances and discover the accelerating expansion of the universe driven by dark energy. The prevailing theory for what triggers this explosion is that the white dwarf accretes so much matter from its companion that it approaches the Chandrasekhar limit, a critical mass of about 1.4 times the mass of our Sun. At this threshold, the pressure in its core becomes so extreme that carbon fusion ignites uncontrollably, tearing the entire star apart in a matter of seconds. The triple star scenario offers a compelling and perhaps dominant pathway to reach this limit. In a standard binary system, the mass transfer process can be unstable. The donor star might swell up as it loses mass, or the eruption of a nova might blow away more material than is accreted, preventing the white dwarf from ever reaching the Chandrasekhar limit. However, the presence of a third star changes the game entirely. By keeping the binary pair on a tight leash, it ensures a high and sustained rate of mass transfer. It can also stabilize the donor star against swelling, creating a more efficient and steady flow of matter onto the white dwarf. This gives the white dwarf a much better chance of steadily growing in mass until it crosses the fatal threshold. Furthermore, if the tertiary companion itself eventually evolves and transfers mass to the inner binary, it could provide a final, massive infusion of material that pushes the white dwarf over the edge. The evidence for this is still building, but it is persuasive. Population studies show that the rate of Type Ia supernova is higher in environments where triple star systems are common, such as the bustling centers of galaxies. Additionally, the chemical signatures of the debris from these explosions sometimes suggest a long and complex accretion history, consistent with the dynamic environment of a triple system. While the classic binary model remains viable, the triple star pathway elegantly solves several of its theoretical problems, providing a robust mechanism to create the conditions for one of the universe's most definitive cataclysms. If confirmed, it would mean that the third star is not just a catalyst for nova, but a key architect of the cosmic explosions we use to map the large-scale structure of the entire cosmos. As we've seen, the gravitational interplay in triple systems can lead to stellar vampirism, cataclysmic explosions, and even the creation of hyper-precise pulsar clocks. But the influence of a third star can also sculpt some of the most breathtakingly beautiful structures in the cosmos. This brings us to our 29th discovery, the creation of spectacular bipolar planetary nebulae. A planetary nebula has nothing to do with planets. It is the final, glowing shroud of a dying star. When a sun-like star exhausts its nuclear fuel, it gently puffs off its outer layers, leaving its hot core exposed. This core, now a white dwarf, floods the expanding cloud of gas with ultraviolet radiation, causing it to glow in vibrant colors for a few tens of thousands of years. In a single star system, this often results in a simple, spherical nebula. But when the dying star is part of a multiple system, the outcome is far more dramatic and structured. In a triple system, the complex orbital dynamics provide the perfect mechanism to shape the outflowing gas into an intricate, often bipolar form. Two lobes of material jetting out in opposite directions like a cosmic hourglass. The most likely scenario involves the dying star having a close binary companion. As the primary star swells into a red giant, its outer atmosphere becomes gravitationally bound to both its own core and to the companion star. The material doesn't escape evenly in all directions. Instead, it is funneled by the gravitational whirlpool of the binary orbit, concentrating the outflow toward the poles of the system and creating two powerful jets. Now introduce the third star. Its distant but persistent gravitational pull can torque the inner binary's orbit, potentially tilting the entire system. This external influence can stabilize or enhance the jet-producing mechanism, leading to a nebula that is not only bipolar but also beautifully symmetrical, with intricate rings and knots that testify to the precise choreography of the three stars. These nebulae, such as the famous Butterfly Nebula, are therefore not just random explosions. They are fossilized records of the orbital dance that govern the star's final moments, with the third star acting as the master sculptor. While a planetary nebula marks the peaceful end of a star's life, a far more violent stellar collision can set the stage for an entirely new beginning. Our 30th discovery ventures into the realm of theoretical prediction, the possibility of second-generation planet formation. Imagine the scenario we discussed earlier with blue stragglers, two stars in a tight binary, driven to merge by the gravitational perturbations of a third. The collision is colossal, flinging a tremendous amount of gas and dust, the shredded material of both stars, out into space. This debris, now enriched with heavy elements forged deep within the stellar interiors, expands into a vast hot disk surrounding the newly merged star. For a long time, astronomers thought such an environment would be far too hot and violent for planets to form, but recent simulations suggest otherwise. This theoretical debris disk is different from the pristine disks around young stars. It is a second-generation disk made from the processed remains of mature stars. As it expands and cools, the conditions within certain regions of this disk may become surprisingly hospitable for planet formation. Dust grains within the cloud would begin to collide and stick together, eventually building up planetesimals and potentially full-fledged planets. These would be truly alien worlds born from the ashes of a stellar catastrophe. Their composition would be incredibly rich in heavy elements like carbon, oxygen, and silicon, making them likely far denser and rockier than any planets in our solar system. A planet forming here would orbit a star that is itself a product of a violent merger, a star that appears paradoxically youthful due to its recent rebirth. While we have not yet definitively found a planet in such a system, the prediction is powerful. It suggests that planet formation is not a one-time event that only happens in a star's youth. It can be rebooted by stellar death and rebirth, with the initial trigger for the merger often being the unseen hand of a tertiary companion. Finally, we come to a discovery that provides a chilling glimpse into the ultimate fate of planets in these turbulent systems. Our 31st strange finding involves a white dwarf with a bizarrely oxygen-rich atmosphere. White dwarfs are the Earth-sized cores of dead stars, and their immense gravity causes heavy elements to sink rapidly out of their atmospheres, leaving behind almost pure hydrogen or helium. So, when astronomers see signs of contamination, elements like oxygen, magnesium, and iron in a white dwarf spectrum, it's a clear sign of recent pollution. Something is currently raining rocky material down onto the dead star's surface. The leading explanation is that this debris comes from asteroids or even entire planets that were torn apart after the star's death. Here's how it likely happens. When a star like our Sun dies, it goes through a red giant phase, swelling to engulf and vaporize any inner planets. For a planet in a stable orbit within a hierarchical triple system, this event is catastrophic enough. But the presence of the third star can make the situation infinitely worse. As the host star swells, its gravitational pull on its planets weakens. The distant third star, however, maintains its steady pull. This can destabilize the orbits of surviving outer planets, throwing them into chaotic, elliptical paths that bring them dangerously close to the white dwarf corpse. The tidal forces near a white dwarf are so unimaginably strong that they can rip a solid, rocky planet apart, stretching and compressing it until it shatters into a cloud of dust and debris. This debris then spirals inward, painting the white dwarf's atmosphere with the elemental signature of a destroyed world. The discovery of a white dwarf like SDSS-J 1242, with an atmosphere dominated by oxygen and other rocky material, is therefore a forensic report of a planetary murder. The unique ratios of elements act as a chemical fingerprint, telling us that the accreted material was once part of a differentiated body, a planet that had a core, a mantle, and a crust much like Earth. The fact that we see this pollution at all indicates the destruction was recent in astronomical terms. While this tragic fate can befall planets around single stars, the gravitational nudges from a third star dramatically increase the probability of such instabilities, turning a stable system into a planetary graveyard. It's a sobering reminder that the long-term survival of a world is never guaranteed, especially when its sun has siblings whose silent gravitational influence can, billions of years after the system formed, finally reach out and trigger an apocalypse. Peering into the heart of a tight triple system where stars whirl around each other in a blur of motion presents an immense challenge. Their light blends into a single, unresolved point in even the most powerful conventional telescopes. This is where a revolutionary technique, long baseline optical interferometry, performs what seems like magic. Imagine taking two or more telescopes separated by hundreds of meters and combining their light with such exquisite precision that they act as a single gigantic mirror. This virtual telescope can achieve a resolution so sharp it could, in theory, distinguish two car headlights on the Moon. When trained on a close triple system, this method doesn't just infer the presence of stars, it can actually resolve them, creating a direct image of the stellar dance. We see not a single blob of light, but distinct points, their positions shifting minutely over nights or weeks, allowing us to map their orbits with breathtaking directness. It's like moving from hearing a crowded, noisy room to having a crystal-clear video of the individual people conversing inside. While interferometry gives us a direct visual, another method uses the universe's own built-in clocks to uncover hidden companions with incredible precision. In a close eclipsing binary, the two stars pass in front of each other from our viewpoint with a regularity that can rival atomic clocks. The timing of these eclipses is exquisitely sensitive to any gravitational influence. If a third, unseen object is orbiting the pair, its gravitational tug will cause the entire binary to wobble in space. This tiny motion means the light from the stars has to travel a slightly longer or shorter distance to reach us, causing the eclipses to occur a few seconds early or late in a predictable cycle. This technique, known as eclipse timing variations, is so sensitive it can detect the gravitational signature of a planet, a brown dwarf, or even a stellar mass black hole. The eclipses serve as the ticking hand of a stopwatch, and any persistent drift in that ticking betrays the mass and orbit of the hidden timekeeper, allowing us to weigh dark objects with a precision other methods struggle to match. This pursuit of hidden worlds, however, runs into a significant obstacle when a third star is shining brightly in the system. When searching for exoplanets using the transit method, looking for the tiny dip in a star's brightness as a planet crosses its face, the presence of third light creates a serious complication. If the star being monitored is part of an unresolved triple, the light we collect is a blend from all three stars. When a planet transits one star, causing its light to dim by, say, 1%, that dip is diluted by the unchanging light from the other two stars. From our perspective, the overall dimming of the combined light might only be 0.3%, making the signal much weaker and harder to detect. This dilution effect makes small, Earth-sized planets incredibly difficult to find and can cause us to underestimate the size of larger planets we do detect, as the transit depth is no longer a true measure of the planet-to-star size ratio. The solution to this problem requires a multi-pronged observational approach. Astronomers must first confirm the multiplicity of the system using other techniques, like direct imaging or speckle interferometry, to identify and characterize all stellar components. Once the amount of contaminating third light is quantified, the transit data can be corrected. The observed shallow dip is scaled up to reveal the true depth of the transit relative to its host star alone. This painstaking process is crucial for obtaining accurate measurements of a planet's radius, which is a key factor in determining its density and potential composition. A world thought to be a large, puffy gas giant might, after correcting for third light, turn out to be a denser, rocky super-Earth, completely changing our interpretation of its nature and habitability. Beyond the subtle timing of eclipses and the dilution of light, there is a more fundamental way to detect a star's unseen dance partners, by watching it sway back and forth across the sky. This is the science of astrometry, the precise measurement of a star's position. For centuries, this was a painstaking manual process, but missions like Gaia have revolutionized the field. Gaia is meticulously mapping the positions, distances, and motions of over 1 billion stars with micro-arcsecond precision. This is equivalent to measuring the diameter of a human hair from 1,000 kilometers away. As a star moves through space, the gravitational pull of an unseen companion will cause it to trace a slight wavy path around their common center of mass rather than a straight line. When that companion is part of a more complex system, the path becomes a rich tapestry of motion. For a triple system, the primary star's wobble is a superposition of two distinct cycles: the short period wobble induced by a close binary companion and the long, slow arc caused by a more distant third star. By fitting a detailed model to the star's meandering path across the celestial sphere, astronomers can not only confirm the existence of both companions but also determine their masses and orbital periods with extraordinary accuracy. Astrometry provides a purely geometric solution to the puzzle of multiple star systems, mapping their orbits in real space. It is a powerful reminder that the cosmos is in constant, intricate motion, and by measuring these tiny stellar footsteps, we can unveil the invisible architecture of gravity that binds them together. To truly understand the destiny of these stellar families, we must journey back to their very beginnings, to the dark wombs of gas and dust where they first ignite. Powerful infrared telescopes like the James Webb Space Telescope allow us to peer deep into these stellar nurseries, and what they reveal is astonishing. We can now observe newborn triple stars still swaddled in their natal cocoons, their faint light piercing through the veils of dust that shrouded their birth. These observations provide the clearest evidence yet that triple systems can form directly from a single collapsing cloud. As a vast cloud contracts under its own weight, it doesn't always split neatly in two. Turbulence and rotational forces can cause it to fragment into three distinct cores almost simultaneously. Each core draws in material, growing into a protostar, all while engaged in a delicate gravitational ballet from their very first moments. Seeing these infant triples confirms that their complex dynamics are not merely a product of later chaotic encounters, but are often an intrinsic part of their origin story. A blueprint for a life of gravitational interdependence written in the first moments of their existence. Yet, not every triple system is born as a single family. In the bustling, crowded environments of globular clusters or the dense centers of young open clusters, a different origin story unfolds, one of celestial adoption. Here, stars are packed so tightly that close gravitational encounters are a regular occurrence. Through sophisticated computer simulations of these dense environments, astronomers have found compelling evidence that a significant number of triple systems are not born together but are assembled through a process of dynamical capture. Imagine a binary star system drifting through the cluster. A single, solitary star passes just a little too close. In the complex gravitational exchange that follows, energy is transferred, and the single star can be captured, becoming bound to the binary pair. This capture event is often temporary and chaotic, but in some cases the new configuration finds a stable, hierarchical arrangement, forging a triple system from stars that began their lives in completely different parts of the nebula. This pathway to multiplicity underscores the dynamic and social nature of star formation in the galaxy's most populous neighborhoods. Regardless of their origin, the life of a tight triple system is a precarious balance, and that balance can be shattered by the most violent event in a star's life, a supernova explosion. When the most massive star in a close triple reaches the end of its life, it does not go quietly. It collapses and explodes, ejecting a huge fraction of its mass into space in a cataclysmic blast. In an instant, the gravitational anchor of the system is violently removed. More importantly, if the explosion is not perfectly symmetrical, the dying star can receive a powerful kick from the blast, rocketing its newly formed neutron star or black hole core across space at hundreds of kilometers per second. In a tightly bound triple, this sudden loss of mass combined with the explosive kick is almost always catastrophic. The system's delicate gravitational equilibrium is obliterated. The most common outcome is a rapid and dramatic disintegration. The supernova's remnant is often ejected on its new high-velocity trajectory, while the two surviving stars, now suddenly freed from the bonds that held them, are flung apart, each sent flying on their own separate paths across the galaxy. A once coherent family is scattered to the interstellar winds, its members becoming runaway stars, their shared history erased by a single terminal flash. However, there exists a more peaceful, though far rarer, path to old age. In a widely separated, hierarchical triple system where a close binary is orbited by a distant third star, the death of one member does not necessarily spell utter destruction. If the orbits are wide enough, the supernova explosion of the most massive star can occur without completely disrupting the system's overall structure. The sudden mass loss will certainly alter the orbits, puffing them out and making them more eccentric, but the gravitational bonds can remain intact. What emerges from the ashes is a truly ghostly configuration, a triple system of stellar corpses. The most likely outcome is a hierarchical triplet containing, for example, a white dwarf and a main sequence star in a close orbit, with a neutron star circling them both from a great distance. Over billions of years, as the other stars eventually die, this system could evolve into a collection of white dwarfs, or even a neutron star binary with a white dwarf companion. These ancient, dark systems are the quiet survivors, cosmic graveyards that have weathered the violent deaths of their suns, their gravitational dance persisting on into the practically infinite future, a silent testament to the enduring architecture of hierarchy in a chaotic universe. But the serene longevity of these ancient systems is the exception, not the rule. For any planets that manage to form within a triple star system, life is a constant battle against gravitational chaos, and our next discovery reveals one of the most insidious threats. A planet orbiting one star in a wide triple faces a danger that operates on a timescale of millions of years, periodic gravitational shaking from the distant stellar duo. Imagine a world like Earth peacefully orbiting its sun. Far away, the other two stars in the system orbit each other, but their path is not a perfect circle. Its orientation slowly rotates or precesses over immense timescales. When their elongated orbit aligns in just the right way relative to the planet's solar system, their combined gravitational pull can reach a peak intensity. This subtle, rhythmic pull acts like a cosmic hand, gently stirring the vast reservoir of icy bodies at the outer edges of the planetary system, a region akin to our own Oort cloud. The consequence of this stirring is a celestial downpour. The gravitational nudge perturbs the orbits of countless comets, sending a significant fraction of them plunging inward on long, elliptical paths toward the inner planets. For a brief geological period, the inner system would be bombarded by a dramatically increased rate of comet impacts. On a world that had developed life, this would be an epoch of fire and upheaval. A single large impact is devastating enough, as evidenced by the dinosaur extinction on Earth. A sustained shower of such events could trigger a series of extinction pulses, repeatedly resetting the evolutionary clock and making the rise of complex, intelligent life an almost impossibly difficult challenge. This mechanism provides a grim solution to the Fermi paradox within multi-star systems. The reason we might not find other civilizations is that their planets are periodically sterilized by comet showers orchestrated by the silent, rhythmic dance of their multiple suns. This gravitational pumping doesn't just affect distant comets, it can directly manipulate the orbit of a planet itself in a far more dramatic fashion. Astronomers have discovered worlds in triple systems whose paths are so wildly eccentric they defy conventional understanding. The key to this bizarre behavior is once again the Kozai-Lidov mechanism. In this scenario, the planet orbits one star while the other two stars form a binary that circles them both. The gravitational influence of that outer binary acts as a constant perturber. Instead of gently stirring comets, it engages in a sustained gravitational conversation with the planet's orbit. The mechanism works by trading off different orbital characteristics. The planet's orbit can remain roughly the same size, but its eccentricity, how oval-shaped it is, and its inclination, its tilt relative to the binary's plane, oscillate in a linked cycle. What this means for the planet is an existence of extreme climate swings that are almost unimaginable. For most of its long year, the world might follow a relatively normal path. But as the Kozai cycle reaches its peak, the planet's orbit is stretched into an extreme ellipse. It will swing breathtakingly close to its host star in a scorching close pass before being flung out to the frigid depths of the outer system. A year on this world could involve a brief, searing summer where oceans boil, followed by an eons-long winter where the atmosphere freezes solid and falls as snow. Life, if it could cling on at all, would need to be incredibly resilient, perhaps existing deep underground or in hibernation for the vast majority of the planetary year. The discovery of such a world demonstrates that the concept of a habitable zone is not a stable ring but can be a dynamically changing, fleeting condition in a multi-star gravitational field. For some unfortunate planets, the gravitational turmoil of a triple system offers no stable outcome at all. Sophisticated computer simulations of planetary formation in these environments reveal a stark truth. Triple stars are exceptionally efficient factories for producing rogue planets. The process often begins during the system's youth. As the three young stars jostle for position in their unstable dance, their gravitational forces crisscross the protoplanetary disk. A planetesimal or a young planet forming within this chaotic environment can find itself on a path that takes it too close to one of the stars. Instead of being captured into a stable orbit, it receives a gravitational slingshot, a kick of energy that flings it out of the system entirely at high speed. This ejection can happen gradually through a series of smaller perturbations or in one sudden catastrophic encounter. These simulations show that a single triple system can eject multiple planets over its lifetime, contributing significantly to the vast population of free-floating worlds now believed to drift in the darkness between the stars. These rogue planets are eternal nomads, their sunless surfaces freezing to temperatures near absolute zero. Any heat they retain comes only from their internal radioactive decay or the faint pressure of gravitational contraction. Yet there is a tantalizing possibility. If such a rogue planet had a thick, hydrogen-rich atmosphere and a subsurface ocean warmed by geothermal activity, like Jupiter's moon Europa, but on a planetary scale, it could, in theory, harbor life in an isolated, dark abyss, completely independent of starlight. The triple star systems that so efficiently create these orphans may be indirectly seeding the galaxy with the potential for life in the most unexpected and lonely of places. For those planets that do manage to hold on to an orbit, the climate they experience is unlike anything we can conceive. The changing pattern of light from multiple suns creates exotic seasonal cycles that operate on overlapping timescales. Consider a planet in a hierarchical system orbiting the primary star. Its most basic day-night cycle and year are defined by this central sun. But the distant binary pair adds another layer of complexity. As they orbit each other over a period of months or years, their combined brightness in the planet's sky will vary. There will be times when both are on the same side of the planet, contributing their light, and other times when one is visible at night and the other during the day, or both are below the horizon. Furthermore, as the binary stars orbit each other, their distance from the planet changes, causing their apparent brightness and heat contribution to wax and wane. This creates a climate with rhythmic pulses superimposed on the main seasonal cycle. A decade-long period of brighter, warmer nights caused by the binary's configuration might be followed by a decade of darker, colder nights. If the planet has any axial tilt, its traditional seasons would be modulated by this external stellar rhythm. Weather patterns would become incredibly complex, with atmospheric circulation models having to account for three separate, moving sources of energy input. The concept of a predictable climate, which was so crucial for the development of agriculture and civilization on Earth, would be absent. Life would need to adapt to a world where the rules of temperature and light are constantly being rewritten by the celestial dance overhead. a testament to the fact that in a galaxy rich with multiple stars, the very definition of a normal environment is stretched to its absolute limit. Peering into the far future of a triple star system is a task that defies simple calculation, but it is not an impossible one. This brings us to our 44th discovery, where astrophysics meets the raw power of modern computing. To understand the ultimate fate of these gravitational dances, scientists turn to some of the most powerful supercomputers on Earth, running simulations of staggering complexity. These are not simple animations, they are numerical experiments that solve the equations of motion for three massive bodies over billions of virtual years, factoring in effects like stellar evolution, mass loss, and general relativity. Each simulation starts with a slightly different initial setup, a minuscule change in a star's starting velocity or position, and watches the consequences unfold. What emerges is a breathtaking panorama of possible destinies. The simulations reveal that the evolution of a triple system is a story of branching pathways, a cosmic choose-your-own adventure where tiny initial differences lead to wildly divergent endings. One pathway leads to a violent merger where two stars are driven together by the gravitational nudges of the third, creating a blue straggler or triggering a cataclysmic explosion. Another pathway ends in a dramatic ejection where the lightest star is flung out into the galactic void, leaving behind a more stable binary. Yet another, rarer path leads to a long-lasting, stable hierarchical configuration that can endure for eons. By running thousands of these simulations, astronomers can create a statistical map of probabilities. They can determine, for instance, that for a given set of masses and initial orbital separations, there might be a 60% chance of an ejection, a 30% chance of a merger, and a 10% chance of long-term stability. This probabilistic view is a humbling acknowledgement that we cannot predict the exact fate of any single real-world system with certainty, but we can understand the range of its possible futures, a crucial insight for interpreting the diverse triple systems we observe in the sky today. But not all triple systems are permanent families. Some are fleeting affairs, cosmic one-night stands dictated by chance. This is the fascinating prediction of our 45th discovery, the existence of temporary triple systems. Imagine a binary star system drifting through a densely populated star cluster. A single, solitary star minding its own business happens to pass a little too close. In the intricate gravitational exchange that follows, the single star can be temporarily captured by the binary pair. For a short period, perhaps a few thousand or even a few million years, the three stars are gravitationally bound, orbiting each other in a chaotic, unstable dance. This temporary union, however, is destined to break apart. The system is not in a stable hierarchical configuration, and the slightest perturbation will cause it to dissolve. The interloping star is almost always ejected, returning to its solitary life, while the original binary pair remains, albeit often with its orbit permanently altered by the encounter. These brief gravitational liaisons are more than just curiosities. They have significant consequences. The close encounter can dramatically reshape the binary's orbit, tightening it or making it more elliptical. This can turn a wide, peaceful binary into a close, interacting pair, potentially triggering mass transfer or setting it on a fast track to a merger. Furthermore, if the binary had a protoplanetary disk, the gravitational tides from the temporary third star would have violently stirred and warped it, perhaps truncating it or triggering a burst of planet formation. The temporary triple system is therefore a potent agent of change, a gravitational spark that can ignite dramatic evolution in a stellar system during a brief but intensely influential flyby. While observing such a transient event directly is challenging, their predicted frequency in star clusters suggests they are a fundamental mechanism for dynamically heating these dense environments and altering the life stories of countless stars. The gravitational influence of a triple system is not confined to its immediate vicinity. It can reach out across thousands of light years to warp the very fabric of spacetime itself, acting as a lens. This is the basis of our 46th discovery. According to Einstein's theory of general relativity, a massive object can bend the path of light passing near it, much like a glass lens bends light. When a foreground star passes directly in front of a distant background star, it can create a microlensing event, a temporary brightening of the background star's light as the foreground star's gravity focuses it toward us. Now replace that single foreground star with a triple system. The resulting gravitational lens is no longer simple. It is a complex, time-varying lens shaped by the combined and shifting gravity of all three stars. As the stars within the foreground triple system orbit each other, their collective gravitational field changes constantly. This produces a microlensing light curve of breathtaking complexity. Instead of a single, smooth peak in brightness, the light from the background star flickers and dances, showing multiple peaks, dips, and asymmetries that are the direct signature of the triple lens's architecture. By meticulously modeling these intricate light curves, astronomers can reverse engineer the system. They can determine the masses of the individual stars, their separations, and their orbital motions, all without ever directly resolving them. This method has proven particularly powerful for detecting triple systems where one or more members are dark, black holes or neutron stars that would be invisible by any other means. The light of a far distant star, twisted and magnified by the invisible hand of gravity, becomes a precise probe, revealing the hidden structure of a triple system we could never see directly. Finally, we arrive at a discovery that links the chaotic dynamics of triples to some of the most powerful explosions in the cosmos. Our 47th finding involves theoretical work that points to triple systems as the potential trigger for a rare and puzzling class of supernova. Standard core collapse supernova mark the death of a single, massive star. However, astronomers have observed supernova with strange properties, excessive brightness, unusual chemical signatures, or evidence of a dense shell of material surrounding the star just before it exploded. These anomalies suggest a more complex prelude to the final blast, and a triple system provides the perfect stage for such a drama. The scenario unfolds in several acts. In a tight triple, the gravitational interplay can drive the two most massive stars to merge. The result is a single, rejuvenated star that is spinning extremely rapidly and is enriched with material mixed up from the stellar interiors. This merged star then lives out its life, but its altered state has profound consequences for its death. The rapid rotation may allow it to retain more of its mass, or it might power a massive magnetic field. When it finally exhausts its fuel and collapses, the explosion is not a standard supernova. It could be an ultra-bright event, a so-called superluminous supernova, energized by the interaction of the blast wave with the dense material shed during the merger process. Alternatively, the chemical pollution from the merger could imprint unusual elemental abundances in the supernova debris, creating a signature that only a stellar merger could explain. In this model, the triple system acts as a crucible, forging a unique stellar object through merger, whose subsequent explosion provides the final, brilliant flash that reveals its violent history. This theoretical connection solves multiple puzzles at once, demonstrating that the path to a star's death can be radically altered by the gravitational company it keeps, turning a triple system into a factory for some of the universe's most enigmatic cataclysms. Our journey through these 50 strange discoveries brings us to the edge of current knowledge, but the most thrilling chapter in the story of triple star systems is the one we are just beginning to write. The next few years promise a revolution in our understanding, driven by a new generation of observatories that will see the cosmos with unprecedented clarity. The James Webb Space Telescope, with its unparalleled infrared vision, is poised to peer deep into the dusty cocoons of stellar nurseries, revealing the birth of countless new triple systems. It will be able to dissect the light from their protoplanetary disks, searching for the chemical signatures of planet formation amidst the gravitational turmoil. Simultaneously, ground-based surveys like the Vera C. Rubin Observatory will embark on a decade-long cinematic portrait of the entire southern sky. Night after night, it will detect the tiny, telltale dips in starlight caused by eclipsing binaries and transiting planets, but its true power lies in the anomalies. It will find stars whose light curves show bizarre, complex patterns that can only be explained by the subtle influence of a third, unseen companion. Instead of studying a few hundred known triples, we will soon have a catalogue of thousands, even tens of thousands. This flood of data will transform our study from one of peculiar individual cases to a robust statistical science, allowing us to finally answer fundamental questions about their formation, stability, and ultimate fate with real confidence. Beyond the realm of light, a new window onto the universe is about to swing open, one that will let us listen to the gravitational rhythms of triple systems. The Laser Interferometer Space Antenna, or LISA, is a future mission that will consist of 3 spacecraft flying in a giant triangle millions of kilometers across. Unlike ground-based observatories that detect the high-frequency chirps of merging stellar mass black holes, LISA is designed to hear the low-frequency hum of the cosmos. This is the domain of systems like tight triplets of white dwarfs or stellar mass black holes within our own galaxy. As these incredibly dense objects orbit each other, they generate a continuous, whispering stream of gravitational waves. In a triple configuration, this signal would not be a simple tone but a complex chord, a superposition of the orbital frequencies of the inner binary and the wider orbit of the third body. The modulation of this signal over time would be a direct readout of the Kozylidov mechanism in action, a pure gravitational fingerprint of the three-body dance. LISA won't just detect these systems, it will precisely measure their masses and orbits, creating a census of dark, compact triples that are completely invisible to traditional telescopes, revealing a hidden population of gravitational engines humming quietly throughout the Milky Way. This brings us to the ultimate and perhaps most profound, strange discovery, the possibility of life under 3 suns. After exploring so much chaos and destruction, we find that in a wide, hierarchical triple system, a peaceful architectural arrangement that can persist for billions of years, the conditions for habitability are not just possible, but could create a worldview beyond our imagination. Picture a rocky planet orbiting within the habitable zone of the system's primary star. Its day-to-day cycle would be dictated by this single sun, much like our own. But the presence of the distant binary pair would transform its sky and its culture. These 2 suns would appear as brilliant, unwavering stars, far brighter than Venus ever appears from Earth. Their light would cast soft, multiple shadows and create a perpetual twilight that never truly deepens into full darkness, even when the primary sun has set. The celestial calendar for any civilization on this world would be astoundingly complex. Their year would be defined by the orbit around their primary sun, but superimposed on that would be the rhythmic brightening and dimming of their sky as the binary stars orbited each other and changed their combined distance. The very psychology of intelligence arising in such an environment is fascinating to contemplate. Their concept of night and solitude would be fundamentally different from ours. Their mythology and astronomy would be built upon a pantheon of 3 deities, their celestial mechanics far more complex from the very beginning. Could such a culture develop a deeper, more intuitive understanding of orbital dynamics and gravitational physics, having such a clear and constant demonstration of a 3-body system in their very sky? The challenges would be significant. Long-term climate stability could be perturbed by the binary's gravitational influence over millennia, but the resilience of life on Earth gives us hope. The discovery that complex organic molecules can form in the disks around young triples suggests the ingredients are there. If life did take hold on such a world, its perspective on the universe would be inherently pluralistic, born under multiple suns. They would gaze into their twilight sky not with loneliness, but with a sense of celestial companionship, a living testament to the fact that the cosmos, in all its chaotic beauty, is a place of vast and varied possibilities. This new era of discovery is not just about building bigger telescopes, it is about forging smarter tools to interpret the cosmic symphony they record. The Vera C. Rubin Observatory, scheduled to begin its legacy survey of space and time in the next few years, represents a fundamental shift in approach. Instead of studying the sky one object at a time, it will conduct a decade-long movie of the entire southern sky, capturing images of over 20 billion galaxies and an estimated 20 billion stars within our own Milky Way. Night after night, its massive 3.2 gigapixel camera will scan the heavens, measuring the brightness of each point of light with incredible precision. For triple star systems, this continuous monitoring is a game changer. The observatory will detect not only the regular dips of eclipsing binaries, but also the far more subtle and complex brightness variations caused by the gravitational and tidal interactions within triple systems. A distant third star talking the orbit of an inner binary, for instance, will create a characteristic repeating pattern of brightening and dimming that will be almost impossible to spot with less frequent observations. The Rubin Observatory will find these signals by the thousands, turning rare curiosities into a vast statistical sample that will allow us to understand the true diversity and commonality of these gravitational dances. The sheer volume of data produced by the Rubin Observatory, however, presents a monumental challenge. We are talking about hundreds of petabytes of information over the decade, far more than any team of human astronomers could ever hope to analyze manually. This is where the power of artificial intelligence and machine learning enters the stage. These are not just buzzwords, they are essential tools for the next decade of astronomy. Scientists are now training sophisticated algorithms to recognize the unique light curve signatures of different types of triple systems. The machine learning model is fed millions of simulated light curves, each representing a different triple star configuration with varying masses, orbital periods, and inclinations. It learns the subtle fingerprints of a system where a third star induces eccentricity oscillations through the Kozai-Lidov mechanism, or the distinct signal of a heartbeat star being gently perturbed by a wide companion. Once trained, these algorithms can sift through the Rubin Observatory's immense data stream with superhuman speed and accuracy, flagging the most bizarre and interesting systems for follow-up study by human researchers. This automated triage will be crucial for discovering the rarest of the rare, perhaps a triple system with 2 black holes and a star, or a configuration where all 3 orbits are wildly misaligned. Machine learning can find these celestial needles in the haystack, patterns so complex and subtle that they might elude even the most experienced astronomer's eye. This synergy of vast data collection and intelligent computation will not only expand our catalog of triple systems exponentially, but will also allow us to classify them in new ways, revealing relationships and evolutionary pathways that we can only dimly perceive today. Beyond the visible light of Rubin and the infrared gaze of JWST, the future holds an even more revolutionary way to study these systems, by listening to the ripples they create in spacetime itself. The Laser Interferometer Space Antenna, or LISA, is a future European Space Agency mission that will open the low-frequency gravitational wave window to the universe. Consisting of 3 spacecraft flying in a perfect triangle millions of kilometers apart, LISA will detect the constant, whispering hum of gravitational waves produced by orbiting systems that are completely invisible to light-based telescopes. For triple star systems, especially those containing ultra-dense objects like white dwarfs, neutron stars, or black holes, LISA will be the ultimate probe. It will hear the gravitational wave signal of a close binary of white dwarfs, and then, superimposed upon that, the subtle modulation caused by a third object orbiting them both. This will provide a direct, exquisitely precise measurement of the system's masses and orbits, entirely independent of the light the stars emit. The data from LISA will be particularly powerful for testing the extreme effects of gravity predicted by Einstein's theory of general relativity. In a tight triple system of compact objects, the gravitational wave signal will carry the clear imprint of the Kozai-Lidov mechanism. We will be able to hear the mechanism working in real time as the gravitational wave frequency shifts and modulates in a predictable pattern dictated by the interaction of all three masses. This will allow for pristine tests of strong field gravity in a regime that is impossible to recreate in any laboratory on Earth. Furthermore, LISA has the potential to discover triple systems that are entirely dark, composed of stellar mass black holes that have long since ceased to emit any significant light. These hidden gravitational families, revealed only by the ripples they create in the fabric of the cosmos, will tell us a completely new chapter in the story of stellar evolution and death, one written not in light but in the silent vibrations of spacetime. But to truly appreciate the symphony that LISA will hear, we need to understand the unique composition of a triple system's gravitational wave signal. A simple binary system, like two black holes circling each other, produces a gravitational wave signal that is elegant in its simplicity. It's a pure, rising tone, a chirp, that increases in both frequency and amplitude as the objects spiral inward, culminating in a final crashing merger. The signal from a triple system, however, is a masterpiece of cosmic complexity. Imagine the inner binary as the string section, producing its fundamental chord, the steady hum of their orbit. Now introduce the third, outer star, as the conductor. Its gravitational influence doesn't just watch, it actively perturbs the inner duo. Through mechanisms like the Kozai-Lidov effect, it periodically torques their orbit, causing their mutual distance to rhythmically pulse. This pulsation directly modulates the gravitational waves they emit. The steady hum of the binary becomes a warble, a frequency-modulated signal that encodes the exact orbital period of the distant perturber. The result is not a single tone, but a rich chord with harmonious overtones. The primary frequency comes from the inner binary's orbit. Superimposed on that is a slower, deeper frequency from the wider orbit of the third body. And then, interwoven throughout, are the subtle modulations caused by their gravitational conversation. The signal evolves not just because the binary is inspiraling, but because the geometry of the entire system is constantly shifting. It's a symphony in multiple movements with themes that repeat and develop over time. Unlike the brief, seconds-long chirp detected by ground-based observatories for stellar mass mergers, the triple system's song can play out for years, even decades, within LISA frequency band. This gives astronomers an incredibly long data stream to analyze, allowing them to disentangle the masses, distances, and orbital parameters of all three bodies with precision that rivals and may even surpass traditional optical methods. LISA's unique sensitivity to these millihertz frequencies makes it the perfect instrument for this new kind of astronomy. This low-frequency band is the domain of systems that are still widely separated, orbiting each other with periods ranging from minutes to years. For a triple system of white dwarfs or stellar mass black holes, this means LISA will detect them thousands or even millions of years before they merge. It's like arriving at a concert during the orchestra's warm-up, giving us a front-row seat to the entire performance leading up to the final crescendo. This long baseline of observation is crucial. It allows us to witness the Kozai-Lidov mechanism in action, to see the eccentricity of the inner binary being pumped up by the third star, and to track how these interactions ultimately drive the system toward its fate, be it a merger, an ejection, or long-term stability. This capability will allow us to move from studying individual, peculiar triple systems to conducting a true galactic census. LISA is expected to detect gravitational waves from thousands of compact binary systems within the Milky Way. A significant fraction of these are likely to have a hidden third companion, their presence revealed only by the distinctive modulation in the gravitational wave signal. By analyzing this population, we can answer fundamental questions. How common are triple systems containing compact objects? What is the typical architecture of these dark families? Does the presence of a third body make the final merger of the inner binary more or less likely? The statistical power of this census will reveal the role triple dynamics play in the life cycle of stars, from their death as supernova to their final end as merging black holes. The silent symphony of gravitational waves, conducted by the unseen hand of a third star, will become a primary tool for mapping the hidden architecture of our galaxy, revealing a universe far more interconnected and dynamically rich than we ever dreamed. As our journey through these 50 strange discoveries comes to a close, we are left with a fundamentally transformed perspective on the cosmos. We began with the simple, beautiful chaos of the three-body problem, a mathematical truth that ensures the dance of three stars is forever unpredictable, a whirlwind of gravitational forces where stability is a temporary truce and violence is an ever-present possibility. We learned that this chaos is not a rare spectacle but a dominant feature of our galaxy, especially for stars like our own Sun, making our solitary solar system the true cosmic outlier. These triple systems are not mere curiosities. They are extreme laboratories and powerful factories, forging everything from hypervelocity stars and cataclysmic supernova to the universe's most precise pulsar clocks and the very building blocks of life itself. The implications for planets and potential life are staggering. A world in a triple system faces a constant battle against gravitational chaos, enduring comet showers triggered by distant stellar partners, wild orbital eccentricities that create millennia-long seasons of fire and ice, and the ever-present threat of being flung into the eternal darkness as a rogue planet. Yet, against all odds, the chemistry for life can begin even there, in warped disks around young stellar triples. The existence of a potentially habitable hierarchical system, our planet orbiting a primary star with a binary pair shining brilliantly in its sky, forces us to expand our definition of home. Life under three suns would experience a reality utterly alien to our own, with a complex celestial calendar and a twilight sky that never truly darkens, shaping a culture with an innate understanding of gravitational interdependence. This grand reevaluation leaves us with a humbling and powerful thought. For centuries, we have looked up at the night sky from our quiet, single-star haven and assumed it represented the cosmic norm. We now understand that this peaceful existence is a fortunate anomaly. The universe, in its vibrant and dynamic heart, is a place of multiplicity, of complex families of stars bound together in a gravitational embrace that is both creative and destructive. Our solar system is not the standard model. It is a sheltered backwater, a tranquil oasis in a galaxy that thrives on the energetic interplay of multiple suns. This realization does not diminish our world but recontextualizes it, making our fragile stability all the more precious and remarkable. So, the next time you gaze up at the seemingly single points of light in the night sky, remember the truth that lies hidden in their brilliance. Many of those stars are not alone. They are the central figures in intricate dances with stellar companions, their gravitational fields orchestrating the birth and death of worlds, triggering colossal explosions and weaving the fabric of space-time itself. The universe is far richer, more chaotic, and more wonderfully strange than we ever imagined. Let this knowledge fuel your curiosity. Stay tuned for the next wave of discoveries, because with powerful new tools like the James Webb Space Telescope and the revolutionary laser interferometer space antenna coming online, the next chapter in this story promises to be the most astonishing one yet. The cosmic dance continues, and we are only just beginning to hear its music.